Before we begin, let me ask you something. What if the universe is not the quiet expanse we imagine? What if the space around you is constantly trembling with motions too small for your senses to detect? If every star and every black hole sends out silent ripples across the cosmos, then what patterns are passing through you right now without leaving the faintest trace? And if space-time itself can twist and stretch like a living fabric, what secrets has it been whispering for more than a century, while humanity only recently learned how to listen? Could it be that the universe has always been speaking, and only now do we finally have the tools to understand its voice? The story of gravitational waves does not begin with a vast observatory or a moment of cosmic violence. It begins with a quiet shift in human understanding during the early years of the 20th century, when Albert Einstein invited the scientific world to imagine gravity not as an invisible force that pulled on distant objects, but as a reshaping of the very stage on which the universe unfolds. Before his work, space and time were seen as separate backgrounds, unchanging and indifferent. They were assumed to be fixed and absolute, a silent container in which matter simply moved. Einstein shattered that picture by showing that mass and energy do not live inside space and time. They sculpt them. They bend the geometry that holds everything together. This idea was not a simple leap of intuition. It arose from years of questioning the nature of motion, acceleration, and light itself. Einstein followed a chain of logic built from confirmed experiments and mathematical consistency. Light, as measured in every careful study of the 19th century, always traveled at the same speed, no matter how fast the observer moved. The equations of electromagnetism insisted on this, yet the mechanics used by scientists at the time could not explain it. Something deeper had to be reworked. This reworking eventually led Einstein to general relativity in the year 1915, a framework that treated spacetime as a connected fabric whose shape is determined by everything it contains. Once spacetime became part of physics rather than philosophy, its behavior could be calculated and tested. The equations predicted more than curved orbits and bending light. They predicted something far stranger. If a massive object moves in a way that disturbs the geometry around it, the disturbance does not remain local. It travels outward at the speed of light, carrying information about the motion that created it. These traveling changes in curvature are what we now call gravitational waves. They are not vibrations of air or energy flowing through matter. They are motions of space-time itself, tiny stretches and compressions that pass through everything without resistance. The idea seemed almost unreasonable when it first appeared. Scientists accepted that the equations allowed these waves, but many doubted that anything in the universe could generate them strongly enough for humans to measure. The waves were predicted to be unimaginably small by the time they reached Earth, far below the sensitivity of any instrument built in the early 20th century. Even if two stars spiraled around one another in a distant galaxy, the resulting ripples would shrink to a scale that seemed lost to detection long before arriving here. That is why, for decades, gravitational waves lived mostly in theoretical discussions. They were mathematically sound, but practically unreachable. Early reactions reflected this tension. Some physicists treated gravitational waves as elegant but irrelevant features of a beautiful theory. Others debated whether the waves were even physical, or if they were illusions created by clever but misleading choices of coordinates. These doubts were not born of ignorance, but of caution. Physics demands evidence, and in those years, no one could imagine how to gather it. The detectors needed to measure such faint distortions did not exist. The lasers, the vacuum systems, and the stable mirrors required for precision measurement were not yet invented. Humanity had only just begun to explore radio waves. Detecting the motion of spacetime itself seemed closer to fantasy than possibility. Yet the equations did not care about human limitations. They continued to predict that every accelerating mass sends out waves. They insisted that binary stars, collapsing cores, merging black holes, and every dramatic cosmic motion must send ripples into the universe. This mathematical certainty kept the idea alive even when technology lagged behind. The scientific community began to re-examine the implications as theoretical tools improved. Calculations became more precise. The behavior of waves in curved spacetime became clearer. The possibility that these waves might be detectable in the far future no longer seemed impossible. It simply demanded a new kind of instrument, one that could measure changes in distance far smaller than any mechanical system of the time. As the 20th century progressed, understanding deepened. Astronomers discovered new classes of stars and binary systems whose motions matched the conditions Einstein had described. Observations of starlight bending near massive bodies confirmed that space-time curvature was real, not theoretical decoration. Step by step, evidence accumulated for the core ideas of general relativity. It became more difficult to doubt the existence of gravitational waves even if none had been directly detected. The theory was too consistent and too successful in every other domain. The waves could not be dismissed. They were an inevitable part of the structure of spacetime. Still, the challenge remained. How do you measure a ripple that changes a length of several kilometers by far less than the width of a proton? How do you detect something that passes through Earth silently, without leaving any trace except a brief and delicate distortion? These questions pushed the scientific world toward a new era, one in which innovation would need to match imagination. It would require technology capable of hearing the faintest whisper ever predicted by physics. And so humanity stood at the edge of a profound transformation. Spacetime had become real. Its waves were mathematically unavoidable. All that remained was to prove that these ripples could be caught, measured, and studied. The path forward would span generations. It would challenge assumptions, ignite debates, and inspire the creation of some of the most sensitive instruments ever constructed. But the journey was now inevitable, because once spacetime was understood as a dynamic fabric, the universe itself seemed to lean in and encourage us to listen. As the idea of gravitational waves settled into the foundation of modern physics, the scientific community began to recognize that accepting their existence demanded more than mathematical confidence. It required a shift in how humanity imagined the universe. If spacetime could ripple, then the cosmos was not a silent ocean, but a restless sea. Every collision of stars, every fall of matter into a black hole, every rapid whirl of a compact pair of objects sent tremors through the vastness. Yet these tremors were so faint by the time they reached Earth that they passed unnoticed through every mountain, every ocean, and every person who ever lived. For generations, these waves washed across our world as quietly as moonlight. The early 20th century held remarkable advances, but even the brightest minds of that time understood that their tools were far from capable of measuring such delicate motions. Telescopes relied on light. Radio receivers relied on electromagnetic waves. Even the most precise laboratory experiments measured forces or mechanical vibrations orders of magnitude larger than the signals predicted by general relativity. The waves Einstein described demanded a sensitivity far beyond any instrument built before the age of lasers. This profound mismatch between theory and capability shaped scientific attitudes for decades. Many respected physicists concluded that while gravitational waves were real in principle, they were essentially undetectable in practice. Because of this, research on gravitational waves progressed slowly at first. It was seen as a domain reserved for theorists who explored the equations for their own beauty, rather than for any practical outcome. Yet curiosity remained alive. Some researchers wondered what might be possible if technology advanced dramatically. They asked whether spacetime itself could be used as a measuring stick. If two beams of light traveled down long paths and returned to meet one another, would a passing gravitational wave stretch one path slightly more than the other? Could the interference of light reveal an almost impossibly small distortion? This idea existed long before it became realistic, but it represented the seed of what future generations would build upon. During these years of slow progress, a deeper understanding of general relativity emerged. Scientists explored how space-time curves in different situations. They calculated the motion of light near massive bodies. They modeled the dynamics of star systems and compared predictions with observations. Bit by bit, the precision of astronomy improved, providing new platforms to test Einstein's theory. The bending of starlight observed during a solar eclipse confirmed that gravity does indeed alter the path of light. Measurements of planetary orbits matched Einstein's predictions more closely than those of earlier gravitational models. Each success strengthened scientific confidence not only in the core ideas of general relativity, but also in its consequences, including gravitational waves. As general relativity continued to prove itself, attention slowly returned to the waves that the theory insisted must exist. The question gradually shifted from whether these ripples were real to how scientists might one day detect them. Theoretical physicists refined the equations describing how waves propagate through space-time. They determined how much energy a binary system would radiate as gravitational waves. They calculated how the orbit of two dense stars would lose energy and shrink over long periods. These calculations suggested that even if no direct detection was possible with the technology of the time, astronomical observations might reveal indirect evidence. This idea was important because it connected gravitational waves to measurable phenomena. If an orbit decayed at the exact rate predicted by Einstein's equations, the loss of energy could only be explained by the emission of gravitational waves. This conceptual bridge between theory and observation marked a turning point. It meant that nature itself might display the effects of these waves in subtle but observable ways. Scientists began to imagine systems in which two compact stars orbited one another closely enough to produce noticeable changes over years or decades. Although such systems were rare and difficult to identify, the universe offered more possibilities than anyone could fully catalogue at the time. Astronomy in the early and mid-20th century was undergoing its own transformation. New instruments opened new windows to the cosmos. Radio astronomy revealed exotic objects that had never been seen with optical telescopes. Among these discoveries were pulsars, rapidly spinning remnants of massive stars. Their regular pulses of radio waves were incredibly reliable, acting as cosmic clocks. When certain pulsars were found in binary systems, their timing offered an unprecedented view into the dynamics of extreme astrophysical environments. The slow tightening of an orbit could, in principle, be measured with extraordinary precision. The development of these ideas gradually set the stage for one of the most important discoveries of the 20th century. Although it belonged to a later chapter in this story, the possibility of measuring orbital decay through pulsar timing proved that gravitational waves were not beyond reach forever. The universe itself provided laboratory conditions far more extreme than anything humans could create. All scientists had to do was observe carefully, interpret faithfully, and avoid the temptation to leap to conclusions not supported by evidence. Each new observational technique allowed more precise tests of general relativity. Each success made gravitational waves harder to dismiss. Meanwhile, on the theoretical front, researchers continued to debate not the reality of the waves, but their subtle mathematical properties. They studied how energy is carried by waves in curved spacetime. They examined how the waves interact with matter, even though the interaction was incredibly weak. These debates were not signs of confusion, but signs of progress. Physics advances by clarifying concepts and ensuring that every aspect of a theory remains internally consistent. The understanding of gravitational waves grew sharper as scholars refined definitions, corrected errors, and built a more robust picture of wave propagation. But even as theory matured, the practical challenge remained formidable. For a wave to be detectable on Earth, it had to come from an event of extraordinary violence. Something had to shake space-time strongly enough that the resulting ripple, after traveling across millions or billions of light years, still carried enough amplitude for instruments to measure. In the language of relativity, This meant systems involving compact objects. Black holes, neutron stars, and supernova remnants became central to the future of gravitational wave astronomy. Without these extreme environments, the waves would be too faint. Yet even the strongest waves arriving at Earth would distort a measuring arm several kilometers long, by a distance far smaller than the width of an atom. This understanding made it clear that humanity would need not just advanced technology, but a radical reimagining of measurement itself. The waves were real, but they were delicate. They whispered rather than shouted. They brushed past planets unnoticed. The question that lingered through the early decades of the 20th century was simple yet profound. Could humans ever build an instrument capable of hearing something so faint? Could the subtle tremor of space-time be lifted out of the noise of Earth's constant motion? The search for answers would require new tools, new ideas, and a new way to listen to the universe. The stage was set, and the world of physics was slowly preparing for an era unlike any that had come before. As the 20th century advanced, the search for a way to detect gravitational waves continued to evolve from a distant hope into a serious scientific question. The idea no longer belonged only to theorists who admired the elegance of Einstein's equations. Engineers, experimental physicists, and astronomers began to ask how the ripple of space-time might reveal itself if the right kind of instrument could be built. This shift from purely theoretical work to practical design represented a turning point in the history of physics. It showed that humanity was slowly inching closer to the possibility of listening to the universe through a method entirely different from light. The path forward did not begin with large observatories. It began with curiosity, with the understanding that if a wave stretches space in one direction while compressing it in another, then two separated objects might experience slightly different motions as the wave passes. The difference would be unbelievably small, but not mathematically zero. If light were used as a ruler, and if the lengths of two paths could be compared, then even the tiniest distortion might produce a measurable shift in the pattern created when the beams reunited. This was the principle behind interferometry, an idea that had existed since the 19th century, long before lasers provided the stability needed to put it into practice. For gravitational waves, the idea required refinement far beyond the instruments of the mid-20th century. Early interferometers were short and not nearly stable enough. They reacted to the slightest vibration, the slightest fluctuation in temperature, the slightest movement of the ground. Earth itself was alive with constant motion from ocean waves, wind, passing vehicles, and even subtle shifting of the crust. Any instrument designed to detect gravitational waves had to overcome this constant noise. It needed a level of precision that had never been approached before. Even the most sensitive tools available in that era fell short by many orders of magnitude. And yet, the progress of technology rarely follows a straight line. The invention of the laser in the 1960s transformed the possibilities of measurement. For the first time, scientists had access to light beams with extraordinary stability and coherence. They could place them in long tunnels, reflect them off mirrors suspended to reduce vibration, and use interference patterns to detect changes in length far smaller than anything previously imagined. With this tool, the idea of a gravitational wave observatory began to emerge from the realm of science fiction into the realm of engineering. Still, the challenge was immense. Even with lasers, the amplitude of a passing gravitational wave would change the length of a kilometer-long arm by less than the diameter of a proton. It was easy for a theorist to write such numbers on paper. It was much harder for an engineer to imagine a machine that could measure them. The early proposals for gravitational wave detectors were ambitious, but they were also fragile. Every environment introduced noise. Every piece of equipment created its own complications. Even the quietest laboratory on Earth was filled with sources of vibration that would overwhelm the faint signal of space-time in motion. But the scientific spirit is built on persistence. Over time, the ideas strengthened. Researchers studied how to suspend mirrors using multiple stages of pendulums to isolate them from seismic motion. They developed vacuum systems that stretched across long tunnels, ensuring that light would travel undisturbed by air. They explored how to stabilize lasers so that their frequency remained consistent across long distances. They investigated how to reduce thermal noise by choosing materials that resisted vibrations at the microscopic level. Each of these innovations solved a small part of the puzzle, and each brought humanity closer to hearing the waves that Einstein had predicted. While engineers worked on instruments, theorists continued to refine the predictions of general relativity. They improved their understanding of how gravitational waves would look when emitted by different systems. They modeled the spiraling motion of compact binaries, the collapse of massive stars, and the merger of black holes. Numerical relativity, a field that used powerful computers to simulate the behavior of spacetime, grew into a major scientific discipline. These simulations were essential because they produced detailed waveforms that described how spacetime would tremble as two massive objects orbited closer and closer before merging. Without these models, scientists would not know what kind of pattern to search for in the data. The combination of theoretical and technological progress transformed the dream of detection from a distant possibility into a growing expectation. By the late 20th century, several teams around the world were working on prototype detectors. These early experiments did not yet have the sensitivity required for detection, but they taught researchers how to handle the challenges of noise and stability. They revealed which techniques worked and which needed improvement. They demonstrated that the task, while incredibly difficult, was not impossible. Step by step, the foundations for large-scale observatories were being laid. At the same time, astronomy continued to provide indirect confirmation that gravitational waves played a real role in the universe. The discovery of binary pulsars showed that their orbits decayed at exactly the rate predicted by general relativity. This decay could not be explained by anything other than the emission of gravitational waves. When the evidence accumulated, the scientific world recognized that Einstein's prediction was not only mathematically correct, but physically real. The waves carried energy away from the system, causing the orbit to shrink. The measurements were precise, consistent, and unmistakable. They formed one of the strongest indirect proofs ever found in support of gravitational wave emission. But again, indirect evidence was not enough to satisfy the full curiosity of physics. Scientists wanted to detect the waves directly. They wanted to measure how spacetime stretched and compressed as a wave passed through Earth. They wanted to observe the exact signature of a distant merger in real time, not through the slow decay of an orbit, but through the trembling of the universe itself. The vision for such a measurement grew clearer with every improvement in technology. The question was no longer whether gravitational waves existed. It was whether humanity could build an instrument sensitive enough to capture them. By the final decades of the 20th century, the answer began to take shape. Plans were developed for observatories far larger and more sophisticated than any interferometer built before. They would require enormous vacuum systems, powerful lasers, mirrors suspended with extraordinary precision, and facilities isolated from as much environmental noise as possible. They would represent one of the most challenging engineering projects ever attempted in the field of experimental physics. Yet the motivation was powerful. If successful, these instruments would open an entirely new way of observing the universe. They would allow humanity to listen to events that produced no light, no heat, and no visible signature. This was the dawn of a new era, one that would soon transform gravitational waves from a theoretical prediction into a measurable reality. But at the end of this chapter, the world still stood in anticipation. The tools were not yet built, the sensitivity was not yet reached. The waves continued to pass through Earth silently, unseen and unheard. The universe whispered, but humanity had not yet learned to listen. The next chapter would change that. It would reveal the debates, the doubts, and the hard-earned evidence that carried the scientific community toward the creation of the first detectors capable of sensing the faint tremor of spacetime. A century of questions would soon meet a century of innovation. the story of gravitational waves entered a strange and turbulent phase as the 20th century unfolded. Einstein had predicted their existence through the logic of general relativity, yet even he struggled with the implications. His equations were clear, but the world they described was so foreign to the intuition of classical physics that parts of the scientific community hesitated to accept the waves as physical. At first, the doubts were simple. How could something so faint, so delicate, be considered a real phenomenon? If no instrument could measure it, and if no experiment could reveal its presence, then perhaps the waves were nothing more than mathematical artifacts buried inside the complexity of curved spacetime. Einstein himself wavered. After deriving gravitational waves from the linearized form of his theory, he initially believed they must exist. But years later, while working with the mathematician Nathan Rosen, he re-examined the equations in a different coordinate system. This led them to an unexpected and troubling conclusion. The waves seemed to vanish. The two researchers prepared a paper arguing that gravitational waves were not physical after all, that they were illusions produced by deceptive mathematical choices. It was a bold claim, one that struck at the heart of the theory Einstein had created. They submitted the paper to a respected scientific journal, and what followed became a legendary moment in the history of physics. The anonymous reviewer, whose identity remained unknown for decades, recognized that the issue was not the theory, but the coordinates Einstein and Rosen had chosen. The reviewer pointed out a subtle but crucial mathematical mistake. The supposed non-existence of gravitational waves was an illusion created by the choice of description. When the problem was transformed into a more suitable coordinate system, the waves reappeared with full clarity. The reviewer urged Einstein to reconsider the claim. This moment marked one of the few times in his career when Einstein faced a direct challenge from peer review. At first, he reacted with frustration, withdrawing the paper and sending it to a different journal. But eventually the error became unavoidable. Einstein acknowledged the mistake, corrected the analysis, and ultimately published a revised version showing that gravitational waves indeed existed. The reversal was significant. It revealed how deeply the mathematics of curved spacetime could deceive even the theory's creator when approached from the wrong direction. The scientific world took note. If Einstein could momentarily doubt gravitational waves, then surely caution was justified. Many physicists continued to debate the nature of energy carried by gravitational waves. Unlike electromagnetic waves, which travel through space and possess well-defined energy density, gravitational wave energy is not localized in the same simple way. General relativity describes energy through mathematical objects, called pseudotensors, which depend on the choice of coordinates. This complexity led to confusion and disagreement. Some researchers argued that if the energy of a wave could not be defined in a straightforward way, then perhaps the waves were not as physically meaningful as they seemed. Yet the deeper the community explored the equations, the clearer the picture became. The waves carried energy in a way consistent with the loss of orbital motion from astrophysical systems. The energy was real, even if its mathematical description was subtle. With time, the debates shifted toward clarity. Physicists recognized that the coordinate-dependent nature of the pseudotensors was not a sign of non-physical behavior, but a reflection of the structure of general relativity itself. By comparing predictions across different reference frames and focusing on observable quantities, scientists built confidence that gravitational waves behaved exactly as Einstein originally proposed. Still, acceptance alone was not enough. Physics demands observation. Without experimental evidence, gravitational waves remained theoretical. The early decades of the 20th century offered no way to detect them directly, but the universe provided a clue through a different phenomenon. During the 1960s and 1970s, astronomers discovered pulsars, extraordinary remnants of massive stars that emitted beams of radio waves with remarkable regularity. These cosmic clocks allowed scientists to measure timing with a precision far beyond any mechanical device on Earth. When a pulsar was found in orbit with another dense object, its pulses revealed the changing shape of the orbit with exquisite detail. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, now known as PSR B1913+16. This system consisted of two neutron stars locked in a close orbit, producing gravitational forces strong enough to shrink their trajectory over time. If Einstein's theory was correct, the orbit would decay at a rate determined exactly by the energy carried away through gravitational waves. If it did not decay, or decayed at a different rate, then general relativity would be in trouble. Years of careful measurements followed. The pulsar's timing never wavered from theoretical expectations. The orbit shrank precisely as Einstein's equations predicted. There was no deviation, no mysterious additional force, no missing energy. The results formed a perfect match with the predicted emission of gravitational waves. This was not a minor confirmation. It was a decisive demonstration that gravitational waves were real and that they drained energy from systems exactly as predicted. In 1993, Hulse and Taylor received the Nobel Prize for this discovery, which provided the first overwhelming indirect evidence of gravitational wave emission. The scientific world now had confirmation that the waves were not mathematical tricks. They were not artifacts of coordinates or inventions of theory. They were physical. They influenced the motion of real astrophysical systems in measurable ways. The only missing piece was direct detection. But this achievement showed that nature itself was already performing experiments far beyond the reach of human equipment. The universe had been producing gravitational waves since its earliest moments, sending them outward from every dramatic cosmic event. The success of the binary pulsar discovery reshaped the narrative. Gravitational waves were no longer theoretical curiosities. They were essential components of the dynamics of the universe. Every orbiting pair of stars, every merging pair of black holes, every collapsing core of a massive star contributed to the cosmic symphony of spacetime. With indirect evidence firmly established, the scientific community turned its attention toward the next challenge. If the waves existed, then surely with enough innovation and perseverance, they could be detected directly. But direct detection remained a formidable quest. The waves were faint beyond imagination, and Earth was filled with disturbances that masked their presence. Yet the evidence from the binary pulsar gave researchers confidence. It meant that the universe was sending ripples strong enough to reach Earth. If instruments became sensitive enough, if noise could be reduced, if vibrations could be filtered out, then the waves would one day be recorded. The realization fueled a new era of experimental ambition. Plans for large-scale detectors began to solidify. The technology required was still being developed, but the motivation had never been stronger. The scientific world stood on the threshold of discovery. Einstein's equations had spoken clearly. Observations had confirmed their predictions. The waves were real, and they awaited detection. Ahead lay the story of the instruments that would bring humanity its first direct encounter with the trembling of space-time. The confirmation from the binary pulsar system marked a profound shift in scientific confidence, but it also intensified the challenge that lay ahead. If gravitational waves were powerful enough to drain energy from orbiting neutron stars, then they were certainly strong enough to reach Earth. The remaining question was whether humans could build a machine sensitive enough to detect the faint tremor of space-time itself. The task required not just ingenuity, but a deeper understanding of how gravitational waves behave, how they influence matter, and how their effects blend into the constant noise of the world. Scientists knew that gravitational waves interacted extremely weakly with everything they passed through. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by matter, gravitational waves simply move through planets, stars, and gas clouds as if they were not there. This made them extraordinary messengers of cosmic events capable of traveling immense distances without distortion. But their weakness also made them challenging to measure. The faint stretching and compressing of space caused by a passing wave was buried beneath far larger disturbances produced by the Earth itself. Any detector had to distinguish the whisper of the universe from the rumble of the ground beneath it. This led researchers to examine every source of noise that might obscure a gravitational wave. Seismic vibrations were the first and most obvious obstacle. Even in a quiet location, the ground is never still. It trembles constantly due to ocean waves, atmospheric pressure changes, storms, and distant human activity. The surface of the Earth shifts by amounts far larger than the distortion created by a gravitational wave. Heat also plays a role. Every material contains thermal motion, tiny jiggles of atoms that create their own noise. Even the light used in an interferometer carries quantum fluctuations that create uncertainty in measurement. Scientists realized that these obstacles could not be eliminated entirely. They could only be reduced and controlled. Understanding these challenges pushed the scientific community to analyze what a gravitational wave would look like when it passed through a detector. The wave would stretch one arm while compressing the other, then reverse the motion as it continued to move outward. The resulting pattern would be a smooth and characteristic curve that mirrored the source that produced it. For binary systems, the pattern would increase in frequency and amplitude as the two objects spiraled inward. This type of pattern, often called a chirp, became central to the design of future detection methods. If an instrument could measure this pattern even faintly, it would be the unmistakable signature of a gravitational wave. But detecting such a pattern required more than just sensitive equipment. It required an understanding of all the ways in which a detector might respond to noise. Scientists began cataloging everything that could mimic a gravitational wave. They studied how wind could shake a building, how temperature changes could expand or contract equipment, how nearby machinery could cause vibrations, and how distant earthquakes could create long-lasting motions. Even the smallest shifts in air pressure or changes in humidity could influence the shape of a detection signal. Every one of these sources had to be accounted for and filtered out, or else a false signal could be mistaken for a real wave from the cosmos. During this period, debates continued about the theoretical foundations of gravitational waves. Some researchers revisited the question of energy transport. Others studied how waves interacted with detectors and how the curvature of space-time altered the motion of mirrors and beams of light. These discussions were not signs of doubt, but signs of progress. They ensured that every assumption was tested and every calculation was precise. They sharpened the community's understanding of what a gravitational wave detection would truly represent. Over time, the theoretical picture became clearer. Scientists developed exact solutions for waves from binary systems and began compiling libraries of predicted waveforms that could later be matched with real data. At the same time, the discovery of pulsars continued to provide invaluable insight. Pulsars with extraordinary timing stability revealed more details about gravitational interactions in extreme environments. Some binary systems displayed irregularities that were studied carefully, not as evidence against general relativity, but as opportunities to refine understanding of astrophysical dynamics. Through these observations, astronomers learned more about neutron star structures, magnetic fields, and the behavior of matter under incredible pressure. These discoveries indirectly supported the existence of gravitational waves by reinforcing the consistency of the theory that predicted them. Meanwhile, new methods of radio astronomy opened a wider view of the cosmos. Observatories across the world discovered pulsars in different environments, some isolated and others in binary systems. With each discovery, scientists placed new constraints on gravitational theories, continuously testing Einstein's prediction that gravitational waves would remove orbital energy at a specific rate. The evidence mounted steadily. It was no longer enough to say that gravitational waves existed. It became necessary to take the next step. The scientific community wanted direct observation. They wanted the ability to watch space-time itself move. This desire coincided with an era of rapid technological progress. Lasers improved dramatically. Vacuum systems became more reliable. Mirrors could be coated with materials that minimized thermal noise. Computers became powerful enough to analyze complex signals and compare them with theoretical templates. Experimental physicists realized that the question was no longer whether gravitational waves could be detected, but when. The technological path forward was difficult but visible. long baseline interferometers began to move from theoretical discussion to practical design. Even so, the memory of Einstein's brief doubt lingered as a reminder that assumptions must always be questioned. The history of gravitational waves was filled with moments of confusion and moments of clarity. The gravitational wave energy debate, the coordinate misinterpretations, the early doubts about detection, all served as lessons that the universe does not yield its secrets easily. It demands precision, patience, and humility. These lessons strengthened the resolve of the scientific community. They approached the challenge with renewed determination, guided by the understanding that the universe often reveals its deepest truths only to those willing to look for them through decades of effort. The progression toward direct detection was not a straight path, but an evolving journey shaped by both theory and observation. Indirect evidence had given a strong foundation, but direct detection would require a leap into an entirely new realm of measurement. It was clear that humanity stood at the threshold of a breakthrough. The tools were nearing readiness. The equations were well tested. The waves were out there, traveling silently through the cosmos. The question that remained was simple and powerful. When would the first one finally be heard? The path toward direct detection took shape slowly, shaped by decades of careful thought and persistent questioning. By the late 20th century, the scientific community understood that confirming gravitational waves required instruments unlike anything built before. The waves themselves were not in doubt. The binary pulsar had shown clearly that energy disappeared from the orbit exactly as predicted by the emission of gravitational radiation. The equations of general relativity remained consistent. Yet despite this progress, gravitational waves still moved through Earth without leaving any trace that human senses or traditional instruments could detect. They were real but silent, present but hidden. Scientists knew that capturing such faint disturbances meant pushing measurement limits to extremes. This challenge encouraged a new era of collaboration. The question was no longer the domain of a handful of theorists or radio astronomers. It required experts in laser physics, optics, vacuum engineering, materials science, and data analysis. Every discipline had something to offer, as the problem touched every corner of modern experimental physics. Spacetime was not an ordinary medium. Detecting its motion required a level of stability that exceeded what most laboratories had ever attempted. Interferometry emerged as the most promising path, but the concept needed to be transformed from a laboratory-scale instrument into an astronomical observatory built on Earth. Early prototypes demonstrated the basic idea, but lacked the sensitivity required for detection. Their arms were too short. Their mirrors were not isolated well enough. Their lasers drifted ever so slightly in frequency. Yet each prototype offered valuable lessons. Scientists learned how to control noise, how to stabilize optical cavities, and how to suspend mirrors so that ground motion was filtered away. As technology advanced, the gap between theoretical sensitivity and achievable sensitivity slowly began to shrink. During this period, debates surrounding gravitational waves continued to evolve. One important discussion centered on how to interpret signals in a world filled with noise. A gravitational wave would stretch and compress space in a pattern that could be predicted, but noise created patterns as well. Vibrations from earthquakes could produce long-lasting motions in the ground. Heavy winds could shake buildings. Even the movement of traffic miles away could leave tiny signatures in sensitive equipment. The community understood that a single detector was not enough. To confirm a gravitational wave, at least two detectors positioned far apart needed to record the same pattern at almost the same time. Only then could scientists distinguish a real signal from local disturbances. This insight led to the vision of a global network of interferometers. If a gravitational wave passed through Earth, it would cause the same stretching and compressing pattern at different locations, separated by a slight delay depending on the direction of travel. This delay would serve as a confirmation, allowing researchers to triangulate the source in the sky. The idea was powerful. But building such a network required unprecedented coordination and funding. Scientists needed to convince entire nations that the pursuit of a whisper in spacetime was worth the immense effort and cost. Convincing others was not simple. For many outside the field, the goal seemed abstract. Unlike telescopes that captured visible light or radio arrays that produced striking images of distant galaxies, gravitational wave detectors would not generate pictures. They would record numbers, curves, and waveforms. They would sense the motion of spacetime with no visual counterpart. But for physicists and astronomers, the potential was extraordinary. Gravitational waves carried information from events that produced no light at all. They offered a window into regions of the universe that remained invisible to every other tool. The possibility of observing black hole mergers, neutron star collisions, and the birth of exotic objects held immense promise. As work progressed on theoretical models, the scientific community grew increasingly confident that gravitational waves from merging compact binaries would be strong enough to detect with sufficiently advanced interferometers. The final orbits of black hole pairs produced rapid and intense disturbances in spacetime, creating characteristic waveforms that increased in frequency and amplitude as the two objects spiraled together. These waveforms, predicted through numerical relativity simulations, were unlike anything produced by environmental noise. They became the fingerprints that future detectors would search for. The refinement of these models required powerful computers and detailed understanding of general relativity. Numerical relativity matured as a field, offering precise predictions that could be matched with real data once detectors became sensitive enough. These predictions included the inspiral phase, where two objects orbit closer and closer, the merger where they collide and form a single black hole, and the ring-down phase when the newly formed object settles into a stable shape. Each stage produced a distinct pattern in spacetime. These patterns were essential because they allowed scientists to recognize genuine signals amidst vast amounts of noise. Alongside the theoretical work, observational astronomy continued to provide supporting evidence. Pulsars revealed the effects of gravitational radiation on binary orbits. Supernova observations hinted at asymmetries that could generate waves. Binary star systems of various kinds were studied to understand how compact remnants might evolve. These observations helped scientists estimate how often gravitational wave events might occur. They provided context for the expected detection rates once the instruments reached full sensitivity. Meanwhile, the engineering challenges intensified. Maintaining a laser beam stable over several kilometers required controlling the environment in ways few laboratories had ever attempted. Temperature needed to remain extraordinarily constant. Vacuum systems had to stretch over long tunnels without leaks. Mirrors needed to hang from fibers that minimized external vibrations. Even minute imperfections in the mirror surfaces could introduce unwanted distortions. Every detail mattered. The detectors were not simply machines, they were sculptures of precision, crafted to reveal a vibration so subtle that it pushed the boundaries of what measurement could achieve. Despite these challenges, scientific optimism grew. The success of the binary pulsar discovery had shown that the universe produced gravitational waves strong enough to notice indirectly. The theory predicted that mergers of black holes and neutron stars would produce far stronger waves. If such an event occurred close enough to Earth, the signal might rise above the noise. Yet the challenge was not only detecting the waves, but distinguishing them from false alarms. Scientists prepared elaborate data analysis techniques, searching for signals that matched the predicted waveforms. They rehearsed how they would respond to a detection, how they would confirm it, and how they would communicate the discovery. By the final years of the 20th century, the momentum had become unstoppable. The groundwork had been laid through theory, observation, and engineering. The scientific community had endured decades of debate, occasionally shaken by uncertainty, yet always guided by evidence. Gravitational waves had moved from fragile predictions to robust components of modern physics. The next step required instruments capable of hearing space-time itself. The world was on the edge of a discovery that would change humanity's understanding of the universe and confirm a prediction first made in the year 1915. The stage was set for the construction of the first large-scale detectors. Soon, the era of indirect evidence would give way to the era of direct measurement. The faint echo of distant cosmic collisions was about to be heard for the first time. Ahead lay the moment when theory and reality would collide, revealing the ripples that had crossed the cosmos for billions of years. Long before the first gravitational wave was detected, the idea of building an observatory capable of sensing the trembling of space-time seemed almost impossible. The waves arriving at Earth were expected to change distances by an amount so small that even the width of a proton looked enormous in comparison. Yet this impossibility did not discourage the scientists who dedicated their careers to the challenge. Instead, it ignited a new ambition. If space-time could move, then humans would learn how to measure that movement. The first seeds of this effort appeared in the mid-20th century, when the idea of using lasers to detect gravitational waves began to evolve from speculation into a practical engineering problem. The concept was elegant in its simplicity. If a gravitational wave stretched space in one direction while squeezing it in another, then the lengths of two long arms placed at right angles to one another would differ slightly as the wave passed. If a beam of light traveled down each arm and returned to a central point, the difference in travel time would reveal the distortion of space-time itself. The challenge was not the principle, but the execution. To measure such an effect, the arms needed to be incredibly long, the laser had to be extraordinarily stable, and the mirrors had to be isolated from nearly every vibration that the Earth could produce. Researchers began testing small prototypes, learning how to stabilize lasers, reduce noise, and control optical paths. These early experiments laid the groundwork for what would eventually become one of the most sensitive measurement devices ever built. The idea grew into a vision for a large-scale observatory, one that would require unprecedented vacuum systems, kilometers of carefully aligned tunnels, and engineering solutions far beyond those of existing laboratories. As the concept matured, it became clear that this effort would require support from national science foundations, collaboration across universities, and the commitment of a generation of researchers. The design that emerged would eventually be known as the Laser Interferometer Gravitational Wave Observatory, or LIGO. It would consist of two facilities positioned thousands of kilometers apart, one in the state of Washington and the other in the state of Louisiana. Each observatory would use two long arms arranged in an L shape, each measuring 4 kilometers in length. Laser light would travel down these arms inside vacuum tubes, reflect off mirrors suspended with extraordinary precision, and return to produce interference patterns sensitive to the slightest change in distance. The goal was simple to describe, but astonishing in ambition. LIGO would need to detect distortions of space-time less than 1/10,000th the width of a proton. Achieving this level of precision called for engineering innovations that stretched the limits of what was technologically possible. The vacuum tubes had to be kept at pressure levels lower than those found in space. The mirrors had to hang from multi-stage suspensions that acted as filters, removing vibrations caused by Earth's constant motion. The laser beam had to be held steady in frequency and amplitude so that even the smallest change in its path length could be measured. Every component needed to work in harmony, because any small instability could obscure the faint signal of a passing gravitational wave. Scientists and engineers worked together to confront challenges that appeared at every stage of construction. Teams developed seismic isolation systems capable of filtering out vibrations from traffic miles away, from distant ocean waves, and from tiny shifts in the ground. They designed mirror coatings that reduced thermal noise by minimizing random motions of particles at the microscopic scale. They built control systems that adjusted the positions of mirrors continuously, keeping the optical cavities perfectly aligned at all times. Each solution required creativity, patience, and absolute attention to detail. Nothing could be left to chance when the waves being measured were so extraordinarily faint. The development of LIGO also required new methods of data analysis. Even if the instrument achieved its planned sensitivity, its recordings would be dominated by noise. To find a gravitational wave, researchers needed to know exactly what patterns to look for and how to distinguish them from disturbances. This required collaboration with theorists who studied how waves from different astrophysical sources should appear. The waveforms produced by binary black holes, neutron stars, and other compact systems became templates. Computers would later compare these templates with real data, searching for matches that indicated a true detection. Without these predicted waveforms, the instrument would be almost blind. As construction continued, the scientific community understood that LIGO would not guarantee immediate success. It was the largest and most sensitive instrument of its kind ever built, and uncertainties remained about how well it would perform. The first generation of LIGO, completed in the early years of the 21st century, served as a crucial testing ground. It operated for several years, refining techniques, identifying noise sources, and proving that large-scale interferometry could achieve the necessary stability. Although the first generation did not detect gravitational waves, it taught scientists exactly what needed improvement. The lessons learned shaped the design of advanced LIGO, an upgraded version with dramatically increased sensitivity. The improvements included stronger lasers, better mirror suspensions, enhanced seismic isolation, and more sophisticated data analysis tools. Advanced LIGO was built upon the foundations of decades of research, transforming the observatory into a machine capable of hearing spacetime with the precision required to detect gravitational waves from distant cosmic events. When advanced LIGO began operations in the year 2015, scientists around the world held their breath. The instrument had reached the threshold predicted to reveal the waves that had eluded detection for a century. Yet even at this stage, success was not guaranteed. The sensitivity required was extreme. The instrument needed to separate the faint tremor of a distant black hole merger from the constant vibrations of Earth. It needed to measure changes in distance smaller than a fraction of a billionth of a meter. The task required patience, careful calibration, and continuous refinement. But the scientific world knew that the moment of discovery could come at any time. The observatory listened through the darkness, waiting for the universe to speak. Humanity had built the first instrument capable of measuring the motion of spacetime itself. In the silence of vacuum-filled tunnels, through beams of laser light, and with mirrors suspended in delicate equilibrium, a new sense had been created. The stage was set for a breakthrough that would mark one of the greatest achievements in the history of science. The creation of LIGO represented more than a technological achievement. It marked a transition in how humanity approached the universe itself. For centuries, astronomy depended solely on light. Telescopes collected visible light, radio waves, infrared radiation, and later gamma rays and X-rays. Each new wavelength revealed aspects of the cosmos that had been hidden before. But all of these forms of observation shared a limitation. They required matter to emit, or block, or scatter something. Gravitational waves were different. They did not depend on surface temperatures, magnetic fields, or the structure of gas clouds. They carried information from deep inside events that produced no light at all. To listen to them required an entirely new way of thinking. This new approach demanded a level of quiet that seemed almost impossible to achieve on Earth. The planet is a restless place. Waves crash against distant shores, sending vibrations that travel hundreds of kilometers. Winds push against mountains and plains, creating pressure changes that ripple underground. Human activity adds its own layers of disturbance, from vehicles to machinery, to the constant movements of cities. Even the ground itself is alive with slow, steady tremors caused by shifting plates deep beneath the surface. All of this motion is far larger than the tiny distortion of spacetime that a gravitational wave would create. To overcome this, LIGO relied on a combination of isolation and control. The mirrors at the ends of the long arms were suspended like pendulums, but not by a single layer. Each mirror hung from a series of carefully designed stages, each filtering out different ranges of vibration. This multi-stage suspension system acted like a set of barriers that prevented ground motion from reaching the mirrors. Even so, the residual motion was still too large, so additional active control systems continuously adjusted the mirror positions, using feedback loops that corrected drift with incredible precision. The laser that powered the interferometer also required extreme stability. Changes in temperature, pressure, or electronic noise could alter its frequency or intensity. To prevent this, the laser was placed inside a carefully controlled environment. Power stabilization systems ensured that the beam remained steady. Frequency control systems kept its wavelength constant. Every fluctuation had to be minimized because even the smallest drift could obscure the signal of a gravitational wave. Then, there was the challenge of the vacuum itself. The long arms of LIGO contained some of the largest vacuum systems ever built. Air molecules, even sparsely distributed, could cause scattering that degraded the laser beam. To avoid this, the pressure inside the vacuum tubes was reduced to a level lower than that found in deep space. Pumps ran continuously to maintain this environment. The tubes were constructed from stainless steel and stretched across kilometers of desert and forest. Their sheer size represented a monumental feat of engineering, one that required years of planning and construction. Despite these challenges, the first generation of LIGO demonstrated that long baseline interferometry could be stabilized at an extraordinary level. Scientists learned how to identify noise sources that had not been predicted initially. They discovered that small creatures walking near the observatory could create measurable disturbances. Trucks driving on distant roads left signatures in the data. Even lightning storms, hundreds of kilometers away, could influence readings. Every one of these signals had to be catalogued, understood, and filtered out. The process of learning how the environment affected the detector was as important as building the detector itself. These early years of operation were essential for shaping the upgrades that became advanced LIGO. For the second generation, nearly every component of the system was redesigned or enhanced. The mirrors became heavier to reduce thermal noise. Their coatings were made using advanced techniques that minimized microscopic vibrations. The laser power was increased so that the light could detect smaller distortions. The suspension systems grew more sophisticated. The seismic isolation platforms became more effective. Computer algorithms improved dramatically, allowing faster and more accurate filtering of noise. By the time advanced LIGO was ready, the scientific community had refined not only the instrument, but also the strategies for analyzing its data. The waveforms produced by numerical relativity simulations served as templates. When the detector recorded data, powerful computers compared the incoming signal with thousands of predicted patterns. Only a match that aligned precisely in frequency, amplitude, and time could be considered evidence of a gravitational wave. This method, known as matched filtering, lay at the heart of the search. The presence of two LIGO observatories was critical. If a signal appeared at one site but not at the other, it was almost certainly noise. But if both detectors recorded the same pattern with a timing difference consistent with a wave passing through Earth, the evidence became compelling. The time difference between the sites could reveal the direction from which the wave arrived. The combination of sensitivity and geographical separation transformed LIGO into a true observatory of spacetime. Over the years of planning, construction, and testing, the scientific world had grown more certain that gravitational waves from astrophysical events were within reach. The equations predicted that merging black holes, especially those with masses larger than typical stellar remnants known before the 21st century, could produce waves strong enough to detect even from distant galaxies. The idea seemed bold, given that no black hole merger had ever been observed through light. Yet the mathematics of general relativity insisted that these events must occur. As advanced LIGO prepared to begin full operations in the year 2015, anticipation filled laboratories around the world. Researchers had refined their methods, debugged their algorithms, and calibrated the detectors with incredible care. They understood the noise. They understood the predicted signals. They believed that the observatory was ready, but no one knew when or if a gravitational wave would be detected. The universe does not operate on human schedules. Cosmic mergers occur in distant galaxies according to their own timelines. Still, something had changed. For the first time in history, humanity possessed the ability to detect the movement of spacetime itself. The detectors rested quietly in their long tunnels, isolated from the Earth, listening through silence for a sign that the universe was about to reveal a secret it had carried for billions of years. The journey had already taken a century of theoretical effort, decades of engineering, and countless refinements. Now the stage was set for a discovery that would alter physics forever. All that remained was for the universe to whisper. The moment advanced LIGO began full observations, the scientific world entered a period of quiet suspense. Each day, the detectors listened to the universe with a sensitivity far beyond anything previously achieved. The instruments rested in their long vacuum tunnels, where lasers bounced back and forth between suspended mirrors, measuring distances so precisely that even the tiniest tremor mattered. The data poured in continuously, an ocean of numbers that captured every vibration, every fluctuation, and every subtle movement of the world. Most of these disturbances came from Earth itself, from storms, distant earthquakes, and the constant shifting of the ground. But hidden within this noise might be the signal the scientific community had pursued for a century. Researchers monitored the instruments from control rooms filled with screens that displayed the health of every component. They examined the laser power, the alignment of mirrors, the temperature of systems, and the behavior of the seismic isolation platforms. Every detail mattered. Even a minor glitch could produce a false alarm. The scientists had trained for years to recognize these moments, to separate environmental disturbances from genuine signals. Their expertise allowed them to anticipate patterns of noise, yet the complexity of the detector meant that surprises could still occur. No one knew when a real gravitational wave would pass through Earth. The universe had been sending them for billions of years, but until now, humanity lacked the means to hear them. Advanced LIGO's first observing run began with optimism, but also with caution. The team understood that the initial months might bring more questions than answers. They expected to refine their noise models, adjust calibration methods, and improve their analysis tools. Although the instrument had reached its design sensitivity, experience had shown that real-world operations always introduced challenges. Yet beneath this practical mindset was a deeper sense of anticipation. Decades of theoretical predictions and indirect measurements had pointed toward a universe filled with gravitational waves. Somewhere out there, massive objects spiraled around each other, sending ripples across space-time. If the detectors were sensitive enough, these ripples would eventually reveal themselves. While LIGO waited, theoretical models continued to evolve. Numerical relativity simulations had reached extraordinary accuracy, allowing scientists to predict how gravitational waves would behave as two black holes approached one another. These simulations showed that the signal would be incredibly faint at first, a slow dance of low-frequency waves as the objects orbited at great distances. As they drew closer, the frequency would rise steadily, producing a distinctive chirp. At the moment of merger, the amplitude would spike, followed by a ring-down pattern that marked the settling of the newly formed black hole. The entire sequence would unfold in less than a second for many systems, yet it carried an enormous amount of information about mass, spin, and the dynamics of curved spacetime. The knowledge of these waveforms provided confidence, but also added weight to the responsibility of distinguishing real signals from noise. Gravitational waves were expected to be rare events, separated by months or years. The detectors would record countless disturbances every day, most of them mundane. The challenge was to identify the unmistakable signature of a cosmic collision hidden in the sea of vibrations. This required extensive data analysis, using matched filtering techniques that compared the incoming signals with thousands of predicted templates. Only a precise match in shape, timing, and correlation between both detectors would indicate a true gravitational wave. In the control rooms, scientists watched the data streams with a combination of routine patience and quiet excitement. They understood that the universe does not perform on command. But they also knew that the detectors were capable of hearing signals from galaxies millions or even billions of light years away. The sensitivity they had achieved meant that even the most distant and violent cosmic events could send detectable waves across space-time and into their instruments. The realization that LIGO could sense the disturbance caused by black holes in other galaxies was both humbling and exhilarating. As the days turned into weeks and the weeks into months, the observatory continued its patient listening. The detectors operated around the clock, interrupted only by brief periods of maintenance or calibration. Teams rotated through shifts, ensuring constant vigilance. Some nights were quiet, while others brought bursts of noise from storms or earthquakes. But the effort never wavered. Every second of operation represented another chance to capture a signal that would rewrite textbooks and confirm one of the last major untested predictions of general relativity. The significance of such a detection extended far beyond theory. It would not simply confirm the existence of gravitational waves, it would open an entirely new field of astronomy. For the first time, humans would be able to observe the universe through the movement of space-time itself. Events that produced no light, that unfolded in darkness and deep gravitational wells, would finally become visible in a new way. The merging of black holes, the collision of neutron stars, and the catastrophic deaths of massive stellar cores would no longer be hidden. Gravitational waves offered a means of seeing into the heart of matter where no telescope could reach. While anticipation built at the LIGO facilities, the global scientific community watched attentively. The success of the binary pulsar had proven that the waves must exist, but direct detection carried a symbolic and scientific weight far greater than indirect evidence. Laboratories, observatories, and universities around the world prepared to respond if a detection occurred. Astronomers readied their telescopes to search for electromagnetic counterparts. Theorists refined their models to interpret the data, and across the entire field of physics, there was a shared understanding that the first detection would mark a turning point, comparable to the discovery of radio waves or the first images of galaxies beyond the Milky Way. It is difficult to describe the atmosphere during these early months of listening. There was tension, but not anxiety, excitement, but not impatience. The scientists involved had spent their lives preparing for this moment. They knew that the universe would reveal a gravitational wave eventually. The question was simply when. Each day the detectors operated was a new invitation to the cosmos. Each night, the long arms stretched across the landscape, silent and waiting, measuring distances with a precision that seemed almost impossible. And above them, far beyond Earth's atmosphere, objects of unimaginable mass continued their ancient motions, sending ripples into the fabric of space-time. Humanity had reached the edge of a historic discovery. The detectors were ready, the waveforms were known, the analysis tools were sharpened. The universe had billions of years of stories to tell. All that remained was for one of those stories to cross the Earth at the right moment and leave its faint trace in the paths of laser light. The first signal was approaching, even though no one yet knew it. When the universe finally chose to reveal its message, it did so quietly. There was no flash of light, no thunderous sound, no visible sign in the sky. Instead, deep inside the long, vacuum-filled arms of advanced LIGO, space-time itself shifted by an amount so small that no ordinary instrument could have sensed it. The event that caused this shift had unfolded more than 1 billion light-years away, long before humans walked the Earth, long before the Sun formed, long before the Milky Way took its familiar shape. Two black holes had spiraled toward one another in a distant corner of the cosmos, drawing closer with each orbit as they radiated gravitational waves into the surrounding universe. For countless cycles, the waves traveled outward, passing through gas clouds, galaxies, and interstellar emptiness until they reached our world. On the morning of the 14th of September in the year 2015, the LIGO Observatory in the state of Louisiana sensed a faint tremor in the interference pattern created by its laser beams. A fraction of a second later, the observatory in the state of Washington recorded the same disturbance. The signals were nearly identical, separated by a small delay that matched the time it took a gravitational wave to travel from one detector to the other. This coincidence was not accidental. It was the exact signature predicted for a gravitational wave passing through Earth. The instruments had captured something real. In the control rooms, nothing dramatic happened at first. No alarms sounded. The screens did not flash with bright colors. The disturbance was small, just another curve in a continuous stream of data. The scientists on shift marked it, noted its characteristics, and continued their work. Only later, when the data were reviewed in detail, did the significance become clear. The signal had the unmistakable form of a chirp. The frequency rose smoothly, the amplitude increased, and the pattern matched precisely what numerical relativity predicted for the final moments of a binary black hole merger. Nothing else in nature, and no known source of noise on Earth, could produce such a shape. Carefully, methodically, and with the cautious discipline that defines physics, the LIGO team began a rigorous investigation. They asked every question imaginable. Could a glitch in electronics produce this pattern? Could a seismic disturbance mimic the waveform? Could a human error or a malfunction be responsible? Each possibility had to be examined and ruled out. The detectors had recorded millions of moments of noise before. But this event behaved differently. The waveform was coherent, smooth, and physically meaningful. It appeared at both observatories, with the timing difference exactly consistent with a wave moving at the speed of light. When matched against thousands of theoretical templates, the signal aligned with extraordinary precision. The team followed strict protocols to ensure objectivity. They checked environmental monitors. They reviewed instrument logs. They compared the signal with known patterns of noise. Nothing matched. The signal remained unique. It carried the clear imprint of two massive bodies spiraling inward. When the researchers used the waveform to reconstruct the event, they discovered that the merging black holes had masses of roughly 36 times and 29 times the mass of the Sun. When they collided, their combined mass became slightly smaller than the sum of the two original objects. A portion of their mass had been transformed into pure gravitational wave energy, carried away through the universe. The amount of energy released in the final fraction of a second was staggering. In that brief moment, the power radiated as gravitational waves exceeded the combined electromagnetic output of every star in the observable universe. Yet by the time the waves reached Earth, they were unimaginably faint, stretching the 4-kilometer arms of LIGO by a distance smaller than the width of a proton. The fact that humanity had built an instrument capable of detecting such a whisper remains one of the most remarkable achievements in the history of science. As the evidence accumulated, excitement grew across the collaboration. Teams at different institutions analyzed the data independently, using different methods and assumptions. Every approach yielded the same result. The signal was real. It matched general relativity with extraordinary accuracy. It was the first direct detection of gravitational waves and the first direct observation of a binary black hole merger. When the scientists finally accepted that they were witnessing something historic, the emotion that spread through the community was a mixture of wonder, relief, and profound gratitude. For decades, gravitational waves had existed only as mathematical predictions and indirect inferences. Now they were real, recorded, and undeniable. Einstein's century-old prediction had been confirmed. The curvature of space-time had moved, and humanity had recorded its motion. The discovery provided not only validation, but also new insight into the universe. The existence of black holes with masses around 30 times that of the Sun had not been expected from earlier observations. The detection revealed a population of massive black holes previously unknown, opening new questions about how they formed. The publication announcing the discovery appeared in early 2016, accompanied by a detailed analysis and the reconstructed waveform. The signal was named GW150914, marking its date of arrival. The scientific world responded with astonishment. News spread rapidly. Researchers across the globe recognized the detection as a turning point in physics. It marked the birth of gravitational wave astronomy, a field that would soon become essential to understanding the universe. But the significance of the moment extended beyond physics. It represented the triumph of patience, precision, and collaboration across generations. It demonstrated that human curiosity, combined with scientific discipline, can uncover truths buried deep in the fabric of the universe. The signal from GW150914 was not merely a measurement. It was a message from a distant corner of spacetime, carried across more than 1 billion years, arriving at exactly the moment when humanity had finally learned how to listen. The moment GW150914 was confirmed, the scientific world found itself facing a profound shift in how the universe could be explored. For the first time, humanity had listened to the tremor of spacetime caused by 2 black holes merging in the distant cosmos. Yet as extraordinary as the discovery was, it marked only the beginning of what gravitational wave astronomy would become. The LIGO collaboration understood that a single detection, no matter how historic, required rigorous examination, replication, and context. Science moves forward not through isolated miracles, but through consistent and repeatable evidence. The team approached this responsibility with the same precision and discipline that had made the detection possible. After the initial excitement, researchers immersed themselves in a deeper analysis of the signal. They explored the waveform in exquisite detail, dissecting every rise, every curve, and every oscillation. The gravitational wave began at a low frequency, reflecting the slow orbit of the 2 black holes before they reached their final descent. As the orbit tightened, the frequency increased at a rate that matched the predictions of general relativity with stunning accuracy. Near the end, the signal rose sharply, a final crescendo as the 2 objects merged into one. Following this peak came the ringdown, a brief period during which the newly formed black hole settled into its stable shape, emitting a fading pattern of waves that revealed the properties of its final state. Each of these stages contained specific information. From the in-spiral, scientists calculated how much angular momentum the system carried. From the merger, they measured the mass lost as gravitational radiation. From the ringdown, they inferred the mass and spin of the final black hole. These numbers, when compared with theoretical predictions, match so well that they provided one of the strongest tests of general relativity ever achieved. The consistency of the waveform with Einstein's equations was striking. There were no deviations, no unexplained anomalies, no contradictions. The signal aligned with the theory from beginning to end. Beyond the physics, the detection revealed practical insight into the nature of black hole populations. Before GW150914, most black holes known to astronomers came from observations of X-ray emitting binary systems, where a black hole accreted matter from a companion star. These systems typically produced black holes with masses around 10 times the mass of the Sun. The 30 solar mass objects in GW150914 were far heavier. Their existence suggested that massive stars in certain environments could collapse without losing as much mass as previously assumed. It opened a new era of questions about stellar evolution, metallicity, and the formation of black holes in the early universe. As the evidence grew stronger, the LIGO team expanded its analysis to ensure the signal was not a rare artifact or coincidence. They created simulated noise signals to test how often random fluctuations might produce something similar. The results showed that the probability of such a coincidence was extraordinarily low. The detection had a significance well beyond the threshold considered reliable in physics. The event exceeded 5 standard deviations of confidence, a level that left no room for reasonable doubt. The community accepted the result as both genuine and transformative. Even so, scientists did not simply celebrate. They sought verification from every angle. Independent teams within the collaboration repeated the analysis using different techniques. The Virgo collaboration in Europe, although not yet operating at full sensitivity, reviewed the findings as well. Their participation highlighted the importance of a global network of detectors. In the years that followed, this network would grow, enabling even more precise observations. But in this early moment, what mattered most was the clarity and coherence of the signal. It provided a foundation upon which the next discoveries would rest. The confirmation of the event triggered a wave of scientific and philosophical reflection. Some researchers revisited old debates about the nature of space-time, marveling at how a century-old prediction had stood so firmly. Others turned their attention to what gravitational wave astronomy could reveal about the unseen universe. Black holes, once considered exotic theoretical objects, now moved into the mainstream of observational astrophysics. Their mergers, once invisible, now produced measurable signals that carried information unavailable through any electromagnetic observation. The discovery also demonstrated the power of collaboration. Hundreds of scientists across continents had worked together for decades to build, refine, and operate the detectors. Engineers designed the vacuum systems, the seismic isolation platforms, and the mirror suspensions. Theorists created the waveform templates. Data analysts developed the filtering algorithms. Each contribution was essential. No single person could have achieved what the community accomplished as a whole. The detection became a testament to the collective strength of scientific cooperation. Outside the scientific world, the discovery captured the imagination of the public. The idea that space-time had vibrated and that humans had measured that vibration resonated deeply. It altered the way many people viewed the universe. The cosmos was no longer silent. It was dynamic and alive with motion. The waves recorded by LIGO were not abstract. They were physical evidence of enormous bodies colliding in a distant galaxy. They were the echoes of a moment that had occurred long before human civilization existed, preserved in the curvature of space-time until they reached the detectors. As the community prepared to publish the detection, the weight of the moment grew clear. The discovery would stand among the greatest in the history of physics, alongside the detection of the cosmic microwave background and the discovery of the expansion of the universe. It would confirm that general relativity remained accurate even in the most violent astrophysical environments, where gravity reached its strongest forms. It would open a new window through which scientists could study events previously hidden from view. Yet the story of gravitational waves did not end with GW 150914. The detection was a beginning, not a conclusion. It marked the birth of gravitational wave astronomy, a field that would soon reveal neutron star collisions, heavy black hole populations, and the detailed internal structure of compact objects. The universe had spoken, and LIGO had heard its voice. Now scientists were ready to listen for more. The months following the detection were filled with careful preparation, anticipation, and refinement of methods. The collaboration continued to search through data collected before and after the September event. If one signal had been captured, others might be hidden within the noise, and indeed, more discoveries lay just ahead. The universe had many secrets left to reveal. The publication of GW 150914 marked a turning point. But within the LIGO collaboration, the sense of achievement was tempered by a deeper awareness that this was only the first step into a vast and unexplored domain. The universe had revealed a single gravitational wave event, yet countless others had already occurred across cosmic history. If the detectors continued to listen, more signals would inevitably arrive. The question was not whether another wave would be detected, but when and from what type of astrophysical source. The team knew that the first detection would transform their understanding of compact objects, but the next signals would begin to reveal patterns, populations, and physical laws that extended far beyond a single merger. In the weeks following the announcement, scientists around the world examined the waveform of GW150914 with growing fascination. It was a perfect match to the predictions of general relativity, but its elegance also raised new questions. How common were such heavy black holes? What environments could produce them? Were they remnants of massive stars formed in low metallicity regions of the early universe? Or did they come from stellar clusters where repeated mergers might occur? No single detection could answer these questions, but it could guide the search. The LIGO collaboration continued refining its analysis tools, preparing for the possibility of more events hidden within the data already collected. Advanced LIGO's first observing run continued for several months after the initial detection. During this time, the detectors recorded a continuous stream of information. Most of it was dominated by noise, but hidden within that noise might be subtle signatures of spacetime disturbances. The scientists expanded their matched filtering techniques, comparing the data with an even larger library of waveform templates. They adjusted their algorithms to identify shorter signals, longer signals, and events with different masses and spins. As they searched, they found hints of possible events that required closer inspection. These were not as loud or clear as GW150914, but they were promising enough to warrant careful analysis. One of these quieter signals would eventually be confirmed as a second gravitational wave event, although its clarity fell short of the first. It showed the merger of another pair of black holes, with masses different from those in the September detection. This event provided further evidence that heavy black hole binaries were not rare. They existed across the cosmos, merging with enough strength to produce detectable gravitational waves. The pattern that emerged suggested that the universe contained populations of black holes, very different from those previously observed through electromagnetic means. LIGO was beginning to reveal the dark side of stellar evolution, a realm hidden from traditional astronomical methods. The collaboration approached every candidate event with remarkable care. They tested the data against environmental monitors to rule out any possible terrestrial cause. They examined the timing, the frequency evolution, and the coherence between the two detectors. The process was meticulous. While the public often celebrated detections as sudden revelations, the reality was far more methodical. Each event required weeks or months of analysis before it could be confirmed with confidence. Scientific integrity demanded nothing less. Gravitational wave astronomy was a new field, and its credibility depended on precision and caution. As more events were identified, scientists began to appreciate the tremendous value of the two separate interferometers. The slight delay between the signals at the Louisiana and Washington observatories provided critical information about the direction from which each wave had arrived. With only two detectors, the sky localization was still limited, forming long arcs rather than precise points. But even this partial information was invaluable. It allowed astronomers to rule out large regions of the sky when searching for electromagnetic counterparts, especially in the case of neutron star collisions. It also confirmed that each detection was cosmic in origin rather than terrestrial. The consistency of timing between the two sites became a defining feature of the reliability of gravitational wave science. The success of these early detections reignited worldwide interest in expanding the gravitational wave network. The Virgo detector in Europe, located in Italy, accelerated its upgrades so that it could join the search during later observing runs. Collaborations formed with astronomers who studied gamma-ray bursts, optical transients, and fast radio bursts, preparing for the possibility that gravitational waves might align with events seen in other wavelengths. This was the foundation of multi-messenger astronomy, a field that would grow rapidly as gravitational wave detections increased. But before that era could bloom, LIGO had to continue refining its understanding of black hole mergers. One of the most remarkable aspects of the early detections was how closely the waveforms aligned with the predictions of general relativity. The in-spiral matched the equations exactly. The merger matched the numerical relativity simulations. The ring-down matched the expected oscillations of a newly formed black hole. There were no unexplained deviations, no hints of alternative theories. The tests reached into regimes of gravity stronger than any previously studied, confirming that Einstein's theory remained accurate even under conditions of extreme curvature and motion. The signals carried the fingerprints of spacetime itself, and those fingerprints matched the predictions first written down a century earlier. At the same time, the data revealed details that had never been observed before. The spins of the black holes differed, suggesting that their formation environments might vary. Some systems appeared aligned, while others suggested random orientations. These properties hinted at the processes by which massive stars formed and died. They offered clues about the environments that produced dense stellar remnants. With each detection, astronomers assembled a clearer picture of the populations of compact objects scattered throughout the cosmos. The universe, once observed primarily through light, now revealed its hidden architecture through gravitational waves. The collaborative nature of the work also grew stronger. Teams across continents exchanged data, theoretical predictions, and analysis methods. The LIGO scientific collaboration became a global effort, with contributions from students, postdoctoral researchers, senior scientists, and engineers. The sense of shared accomplishment deepened with each new discovery. The journey had begun with a single signal, but it was quickly becoming clear that gravitational wave astronomy would transform into a constant stream of cosmic events. As the first observing run concluded, the collaboration prepared for more upgrades and future operations. The lessons learned from the early months guided improvements in calibration, noise reduction, and sensitivity. The detectors would soon listen with even greater clarity, expanding their reach into the distant universe. As they improved, the number of detectable events would rise. The black hole mergers that once seemed exotic and hypothetical were becoming routine. The universe was far more dynamic and violent than anyone had imagined a few decades earlier. The first detection had opened a new era. The subsequent events proved that the era would not be a fleeting moment, but a permanent shift in the way humans explored the cosmos. A century after Einstein first predicted gravitational waves, the trembling of spacetime had become a tool for investigation. A new sense had been added to the human understanding of the universe. Ahead lay neutron star collisions, kilonova explosions, and discoveries that would reshape astrophysics. But at the end of this chapter, the message was clear. The universe had begun to speak through gravity, and humanity had finally learned how to listen. The first detections of gravitational waves revealed more than an extraordinary triumph of measurement. They revealed an unseen universe, a realm of massive bodies colliding in silent darkness, untouched by light and hidden behind layers of space that no telescope could penetrate. Black holes, which for decades had existed only through indirect signatures of X-ray emission or gravitational influence on companion stars, now announced themselves directly through the trembling of spacetime. Their mergers produced waveforms rich with information. Each detection was a message carried across millions or billions of years, encoded not in photons, but in the rhythm of curved geometry. As more gravitational wave events appeared in LIGO's data, a surprising portrait began to emerge. The black holes identified through these signals were heavier than many astronomers had expected. Their masses often exceeded 20 solar masses, sometimes reaching or surpassing 30 solar masses. Before the era of gravitational wave astronomy, most known black holes from X-ray binary systems weighed around 10 solar masses. The discrepancy forced scientists to reconsider long-held assumptions about stellar evolution. Massive stars with low metallicity could retain more mass before collapsing. Environments in the early universe, where stars contained fewer heavy elements, might produce black holes far larger than those commonly found in nearby galaxies. Gravitational waves offered these insights because they measured properties directly from the inspiral and merger. The amplitude and frequency of the waves revealed the masses of the colliding objects. The shape of the signal showed how rapidly they orbited and how their spins influenced the final outcome. The ring-down pattern, the final oscillations emitted as the newly formed black hole settled into equilibrium, allowed scientists to determine the mass and spin of the remnant. These measurements required no light, no temperature readings, no spectral lines. They emerged purely from the dynamics of space-time. For the first time, astronomers could study black holes without relying on electromagnetic radiation at all. But black holes were only part of the story. Neutron stars, the dense remnants of exploded massive stars, played an equally important role in this new era of observation. For decades, neutron stars had been known through radio pulses, X-ray bursts, and occasional gamma-ray flashes. Yet their collisions, predicted by theory, had never been observed directly. Neutron star mergers were expected to produce gravitational waves with distinctive signatures, lower mass systems, longer inspiral periods, and frequencies that rose more gradually before the final collision. They were also expected to produce electromagnetic radiation, offering a rare opportunity to combine gravitational wave and light-based astronomy. Within the gravitational wave community, scientists anticipated that a neutron star merger would produce a signal that lasted longer in the frequency band of LIGO and Virgo. The inspiral of such systems could be observed for tens of seconds, allowing extremely precise measurements of the masses and the tidal deformation of the neutron stars. These details carried profound implications for the equation of state of matter at densities far greater than those found in atomic nuclei. Neutron stars were laboratories for physics that no experiment on Earth could replicate. Their interiors held the answers to questions about how matter behaves under extreme pressure, questions that had remained unresolved for decades. As theorists and experimentalists prepared for such an event, the scientific community also recognized another crucial consequence. Neutron star mergers were believed to be factories for some of the heaviest elements in the universe. Gold, platinum, and many rare elements found on Earth were thought to form through rapid neutron capture processes occurring during explosive astrophysical events. If gravitational wave detectors could identify a neutron star merger, and if electromagnetic observatories could capture the resulting glow, scientists could directly test these predictions. It would reveal how the elements essential to planets and life were forged in cosmic history. The growing confidence in gravitational wave detection also reshaped astronomical strategies around the world. Optical, infrared, radio, and gamma-ray observatories developed rapid response systems designed to follow up gravitational wave alerts. Teams coordinated across continents, preparing to search the sky for the fading glow of explosive events. This global cooperation represented the beginning of a new era known as multi-messenger astronomy, where different forms of cosmic information were combined to produce a deeper understanding of astrophysical phenomena. Meanwhile, every detection continued to refine humanity's understanding of compact objects. Some black hole mergers revealed unusually high spins, suggesting that the objects may have formed in binary systems rather than through dynamical encounters in dense star clusters. Other systems showed spins that appeared randomly oriented, hinting at different formation channels. The diversity of these signals revealed that the universe produced compact binaries in more ways than previously recognized. Each detection added another point to a growing statistical picture, one that highlighted the complexity of stellar evolution across billions of years. With each new gravitational wave, scientists asked deeper questions. How many black hole binaries exist in the observable universe? How often do neutron stars collide? What conditions lead to especially massive black holes? Can gravitational waves reveal the remnants of stars formed in the earliest epochs of cosmic history? These questions were not theoretical speculation. They were grounded in the data that LIGO and Virgo continued to collect. The answers would emerge as the detectors improved, and as more signals filled the catalogue of cosmic events. At the same time, researchers expanded their search for other types of gravitational wave sources. Supernovae, though far more complex and unpredictable, might emit waves during core collapse. Rapidly spinning neutron stars with slight asymmetries could produce continuous gravitational waves detectable through long-term observations. The early universe itself might have generated a background of gravitational waves through violent processes occurring moments after the Big Bang. While these signals remained undetected, their possibility motivated new techniques and future missions that would broaden the scope of gravitational wave astronomy. The invisible universe was beginning to take shape. Black holes, once mysterious and unreachable, now revealed their masses, spins, and behaviors through the gentle tremor they imprinted on spacetime. Neutron stars, dense beyond human comprehension, prepared to reveal the physics of their interiors through forthcoming collisions. Gravitational waves had transformed astrophysics from a study of light to a study of geometry. The cosmos was no longer silent. It was vibrant with motion, and through the detectors spread across Earth, humanity stood ready to listen. This chapter marked the transition from detection to discovery. The universe was unfolding in ways that had remained hidden for all of human history. But the most dramatic revelation, the moment when gravitational waves and electromagnetic light merged into a single narrative, was still to come. A new event waited on the horizon, one that would reshape physics, cosmology, and the understanding of heavy element formation. That moment would arrive soon, and when it did, it would redefine what it meant to observe the universe. The more the detectors listened, the more the universe revealed its hidden population of compact objects. Each new gravitational wave event added a thread to the tapestry scientists were slowly weaving, a tapestry that depicted systems far more diverse and dynamic than earlier generations of astronomers had imagined. With every detection, the invisible universe grew clearer. Black holes no longer existed only as theoretical solutions or as silent engines powering X-ray binaries. They became active participants in a cosmic dance, colliding, merging, and reshaping spacetime in events powerful enough to be heard across immense distances. Yet even as these discoveries unfolded, researchers knew that a deeper and more intricate story was waiting beneath the surface. A story that would involve not only black holes but also neutron stars, kilonova explosions, and the formation of the heavy elements written into the fabric of planets and living organisms. As the first observing runs continued, scientists became increasingly aware that neutron star mergers represented a crucial frontier. These events were expected to produce gravitational waves with more prolonged and complex waveforms extending through lower frequencies and lasting far longer in the sensitive band of LIGO and Virgo, where black hole mergers produced a swift crescendo that ended in less than a second. Neutron star spirals would continue for tens of seconds, allowing detailed analysis of the internal structure of the stars. The tidal forces acting between them would leave imprints on the waveform, offering clues to the equation of state of dense nuclear matter. This was one of the most elusive questions in modern physics. How does matter behave when compressed to densities that surpass those of atomic nuclei? Does it remain as neutrons? Does it transform into quark matter? Does it adopt exotic phases not found elsewhere in the universe? No laboratory on Earth could replicate such conditions. Only neutron stars held the answers. The anticipation surrounding neutron star mergers grew not only from theoretical importance but also from a profound astrophysical significance. For years, scientists had suspected that the universe's supply of heavy elements originated in cataclysmic collisions of neutron stars. These collisions could generate kilonova explosions, luminous and short-lived events powered by the radioactive decay of newly forged elements. The observational signature of such an explosion would include a bright optical and infrared glow that faded over days. Detecting such a glow, combined with a gravitational wave signal, would allow astronomers to directly measure the creation of gold, platinum, and many other elements essential to the chemistry of planets and life. But before such a breakthrough could occur, the gravitational wave detectors needed to refine their sensitivity even further. Early observing runs had revealed several black hole mergers, but neutron star signals were expected to be quieter and more subtle. The detectors needed to reach their full design sensitivity to capture these smaller ripples. This motivated continued upgrades, better calibration techniques, and new data analysis strategies. Researchers around the world prepared for the possibility of multi-messenger detections by coordinating with electromagnetic observatories. Telescopes in space and on Earth stood ready to respond to gravitational wave alerts, scanning the sky for fleeting light that might accompany the waves from merging neutron stars. The collaboration between gravitational wave scientists and electromagnetic astronomers represented a profound shift in the culture of astrophysics. Traditionally, different types of observatories worked independently, each pursuing its own scientific goals. Now, for the first time, they formed a single network that responded collectively to cosmic events. An alert from LIGO or Virgo could trigger optical telescopes, gamma-ray detectors, and radio arrays to scan vast regions of the sky. Through this collaboration, the universe could be studied not through a single messenger, but through many. Gravitational waves carried information about mass, spin, and geometry. Electromagnetic light carried information about temperature, composition, and environment. The combination promised a far richer understanding of cosmic events than either method could provide alone. Even as the scientific community prepared for neutron star mergers, black hole mergers continued to surprise. Some newly detected systems involved black holes with masses that challenged existing theories of stellar evolution. Others showed unusual spin configurations or mass ratios. These discoveries forced astronomers to reconsider how massive stars evolved, how binaries formed, and how interactions in dense stellar environments shaped the outcomes of compact object populations. The diversity of these systems suggested that the universe created black holes through multiple pathways, each influenced by metallicity, environment, and cosmic history. The gravitational wave data also revealed another remarkable feature of these mergers. The final black hole formed in each collision emitted a distinct ring-down signal that corresponded exactly to the normal modes predicted for a Kerr black hole, the type described by general relativity. This provided one of the most precise tests of the theory ever conducted. Even in the extreme gravitational fields of merging black holes, the equations held firm. No deviations were found. The theory continued to match reality with extraordinary precision, reinforcing its position as the most successful description of gravity ever developed. As the catalogue of events grew, scientists began identifying statistical patterns. They estimated merger rates for black hole binaries across the universe. They determined how often neutron star mergers might occur. They used these rates to explore the history of star formation and the evolution of galaxies. These calculations were rooted entirely in evidence from gravitational waves, independent of light-based observations. For the first time, astronomers could map populations of objects that were invisible to every electromagnetic instrument. This new form of observation enriched the understanding of cosmic structure in ways that were not possible before the advent of gravitational wave astronomy. Yet the most transformative moment still lay ahead. The universe had shown black hole mergers with remarkable clarity, but the scientific community awaited the event that would unify gravitational waves and light into a single narrative. That moment would prove essential for understanding heavy element formation, gamma-ray bursts, and the detailed physics of neutron star interiors. Only a neutron star merger, confirmed through both gravitational waves and electromagnetic signatures, could reveal the full picture. It would test theories of matter under extreme density, validate decades of predictions, and open a new frontier in multi-messenger astrophysics. As the detectors continued to listen and the scientific community prepared for rapid response coordination, a sense of anticipation built across the world. The invisible universe had begun to emerge, but its greatest revelation was approaching. A signal was coming, one that would announce not only the collision of two neutron stars, but also the birth of a new branch of science. When it arrived, it would reshape the understanding of cosmic chemistry, the measurement of cosmic expansion, and the nature of extreme matter. Humanity was on the edge of a discovery that would illuminate the invisible universe more completely than ever before. The long-awaited moment that would transform gravitational wave astronomy into a fully unified science arrived with a signal that unfolded differently from every event detected before it. Unlike the brief and powerful chirps produced by merging black holes, this new signal began softly. It rose slowly, building over tens of seconds as two neutron stars spiraled ever closer together in a dance governed by their immense density and the curvature of spacetime. This signal, which would later be named GW 170817, was recorded on the 17th of August in the year 2017. It marked a defining moment, not only for gravitational wave astronomy, but for the entire field of modern astrophysics. The waveform revealed two compact objects with masses far smaller than those of black holes. Their inspiral lasted long enough that scientists could examine minute details in the signal. As the stars orbited one another, tidal forces distorted their shapes. These distortions subtly altered the pattern of the waves, providing clues about the internal structure of neutron star matter. For the first time, physicists could extract information about the density, compressibility, and behavior of matter under pressures so incredible that atomic nuclei were squeezed into exotic forms. The signal alone represented a breakthrough in nuclear physics, offering data that no laboratory on Earth could produce. But this event carried even more significance. Just seconds after the gravitational wave signal reached Earth, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays. The timing was nearly perfect. The gravitational waves arrived first, followed by the gamma ray burst almost immediately afterward. This near simultaneity revealed something profound. The speed of gravity matched the speed of light to within astonishing precision. The two signals had traveled across more than 100 million light-years, yet their arrival times differed by only a couple of seconds due to the astrophysical processes at the source, not due to any difference in propagation speed. This placed one of the strongest constraints in history on alternative theories of gravity. It confirmed that gravitational waves travel at the same speed predicted by general relativity, reinforcing Einstein's model at cosmological distances and in extreme conditions. The LIGO and Virgo collaborations quickly issued an alert to astronomers around the world. Telescopes in every major wavelength began scanning the region of the sky identified by the detectors. Unlike black hole mergers, neutron-star collisions produce abundant electromagnetic radiation. Hours after the event, optical telescopes identified a new point of light in a galaxy known as NGC 4993. This faint glow signaled the presence of a kilonova, the radioactive aftermath of the neutron-star merger. The discovery triggered a global observational campaign unlike any seen before. Infrared telescopes, ultraviolet instruments, radio observatories, and space-based detectors turned toward the event, capturing data across the electromagnetic spectrum. The kilonova's light revealed the chemical processes unfolding in real time. Heavy elements formed in the collision, their radioactive decay powering the brightness that faded over days. Spectroscopic measurements identified signatures consistent with the formation of elements such as gold, platinum, and lanthanides. For the first time, scientists observed the creation of these elements directly. This confirmed a long-standing hypothesis that neutron star mergers serve as one of the primary sources of heavy elements in the universe. The atoms that would one day become jewelry, electronics, and the materials essential to life had been forged in events like GW 170817, scattered across galaxies by kilonova explosions and incorporated into new generations of stars and planets. Meanwhile, radio telescopes tracked the expanding cloud of debris, watching as it interacted with surrounding material. X-ray instruments detected the afterglow of shock waves traveling through space. The multi-messenger nature of this event provided an unprecedented opportunity to measure cosmic expansion. By combining the gravitational wave data with the electromagnetic observations, scientists derived a new value for the Hubble constant, offering an independent method for understanding the rate at which the universe expands. This measurement differed from those based on traditional techniques, deepening one of the most important questions in modern cosmology. Was the universe expanding faster than previously thought? Were there systematic uncertainties in other methods, or was there new physics waiting to be discovered? GW 170817 did not answer these questions, but it offered a new path toward resolving them. The global collaboration that followed the event demonstrated the true power of multi-messenger astronomy. Observatories that normally pursued independent research united around a single cosmic event. The shared data created a coherent picture of the collision, from the initial inspiral measured in gravitational waves to the electromagnetic fireworks seen across the sky. Scientists witnessed the birth of heavy elements, the behavior of matter under extreme pressure, and the accurate matching of gravitational and electromagnetic signals traveling cosmic distances. This unity transformed what would have been a single discovery into a new chapter of scientific exploration. As the afterglow faded over weeks and months, scientists continued to analyze the event. They examined the gravitational waveform for clues about the equation of state of neutron star matter. They studied the kilonova light curves to refine models of heavy element production. They compared the gamma-ray burst with those observed previously, identifying similarities and differences that expanded understanding of astrophysical jets. Every part of the event contained information, and none of it was wasted. The universe had revealed one of its most dramatic processes, and the scientific community had captured every moment with precision. The discovery of GW 170817 signaled a new era. It was the first event in history observed in both gravitational waves and electromagnetic light, confirming predictions that had remained untested for decades. It offered direct evidence for the origin of many heavy elements. It provided one of the strongest tests of the speed of gravity. It opened the door to using standard sirens as tools for cosmology. And it demonstrated that gravitational wave astronomy, once a dream confined to mathematical equations, had matured into a fully integrated science that reached across disciplines. This event did not merely expand the understanding of the invisible universe, it transformed it. Neutron stars, once known primarily through radio pulses, became sources of light and gravity that told a complete story. Black holes, once hidden in silence, revealed their masses, spins, and histories. The universe, once observed only through electromagnetic windows, opened its geometry to human senses. With each detection, humanity gained a deeper understanding of how stars lived, died, and reshaped the cosmos. As this chapter closes, the universe stands on the threshold of even deeper discovery. The next detections will continue to reveal more about compact objects, heavy element formation, and cosmic evolution. And soon, new detectors will broaden this exploration further, listening with greater sensitivity and reaching deeper into the structure of spacetime itself. The collision of the two neutron stars in the event known as GW 170817 marked a new epoch in the study of the universe. But the deeper meaning of this event unfolded gradually as scientists began to examine every detail of the signals it produced. For the first time, gravitational waves and electromagnetic radiation told the same story, each filling in parts the other could not reveal. This unity signaled the beginning of multi-messenger astronomy, a field that would change how humans investigate the cosmos. It proved that the universe speaks through many channels, and that understanding its most dramatic events requires listening to all of them at once. Long before GW 170817 reached Earth, physicists had predicted how such a merger would unfold. They understood that as two neutron stars spiraled inward, they would radiate gravitational waves that grew stronger and higher in frequency. They knew that the moment of collision would generate a burst of gamma rays, that the remaining debris would form an expanding cloud of radioactive elements, and that the optical and infrared glow of the kilonova would fade over days. But predictions alone were never enough. The universe had to provide evidence. When the gravitational wave arrived, it offered a direct measurement of the masses, the orbital frequency, and the tidal distortions that shaped the inspiral. It did not reveal temperature or composition or magnetic fields, but it revealed the geometry of the collision with extraordinary precision. Then the gamma rays arrived. Their detection confirmed that short gamma ray bursts originate from neutron-star mergers, a hypothesis debated for decades. These bursts are among the most luminous events in the cosmos, yet they last only moments, making them difficult to study. The near simultaneity of the signals offered clarity that had been missing from earlier observations. The gamma rays did not precede the gravitational wave, nor did they trail far behind. They were linked by a common cause, arriving with a delay caused not by the nature of the waves, but by the physical processes at the source. This timing allowed scientists to test the speed of gravity with unprecedented accuracy. If gravity had traveled even slightly faster or slower than light, the difference would have been obvious after crossing more than 100 million light-years. Instead, the signals arrived in near-perfect agreement, strengthening general relativity in a way no laboratory experiment could replicate. As the world's telescopes turned toward NGC 4993, the faint blue glow of the kilonova became the next piece of evidence. Optical telescopes watched the light brighten and fade, while infrared instruments observed the slower, redder glow that emerged as heavy elements formed. This sequence matched theoretical predictions for a kilonova driven by radioactive decay. The colors of the light revealed what types of atoms were being produced. Spectra showed the signatures of lanthanides and other heavy elements formed through rapid neutron capture. The collision had created matter that would eventually drift through galaxies, join star-forming clouds, and become part of new planets. This observation confirmed that events like GW 170817 were essential to the chemical history of the universe, filling it with elements that would later shape worlds and living organisms. Meanwhile, radio telescopes observed the interaction of the expanding debris with surrounding gas. This interaction produced a rising radio afterglow that continued for months, allowing scientists to measure the speed of the outflow and the energy released. X-ray observatories recorded the shock waves traveling through space, tracing the environment around the merger and providing clues about the orientation of the neutron-star collision relative to Earth. Each wavelength added to the story, revealing different layers of the event. When combined with the gravitational wave data, these observations formed a complete narrative that extended from the internal structure of neutron stars to the formation of heavy elements and the expansion of the debris cloud. But perhaps the most surprising consequence of GW 170817 came from its role in cosmology. Gravitational waves from neutron star mergers act as what scientists call standard sirens. By analyzing the waveform, they can determine the distance to the event directly. When the position of the source is known from electromagnetic observations, the relationship between distance and redshift provides a measurement of the Hubble constant, the quantity that describes the expansion rate of the universe. The value inferred from GW 170817 differed from those obtained using traditional methods, deepening an ongoing puzzle known as the Hubble tension. While this single event could not determine which measurement was correct, it demonstrated that gravitational waves could offer an independent pathway for resolving one of the most important questions in modern cosmology. Within the scientific community, the excitement surrounding GW 170817 was unlike anything seen in recent decades. Every group involved in the observation had captured a different aspect of the event, yet all these pieces fit together seamlessly. Astronomers, physicists, nuclear theorists, and cosmologists collaborated to interpret the data. The event touched nearly every subfield of astrophysics, offering a rare opportunity for unified discovery. It deepened the understanding of extreme matter, confirmed decades-old predictions, and opened new avenues of research that would continue for years to come. The success of this multi-messenger campaign underscored the importance of global coordination. Gravitational wave alerts were now shared rapidly with observatories around the world, allowing them to react within minutes. Networks of telescopes designed to scan large regions of the sky became essential partners in identifying electromagnetic counterparts. Space-based instruments recorded high-energy emissions, while radio arrays tracked the slower evolution of the debris. This interconnected approach transformed the way science was conducted. The universe could now be observed through multiple senses at once, revealing details that had remained hidden since the birth of modern astronomy. As the afterglow of the event dimmed and the collaboration released its findings, one fact became clear. Multi-messenger astronomy was not merely a new technique. It was a new language for interpreting the cosmos. It allowed scientists to connect the geometry of spacetime with the chemistry of matter, the physics of dense objects with the large-scale structure of the universe, and the death of stars with the creation of elements. The discovery reshaped the scientific landscape and set the stage for future observations that would explore even deeper mysteries. This chapter marks the moment when gravitational waves and electromagnetic light combine to reveal the universe in its fullest form. Ahead lay further detections, greater sensitivity, and instruments designed to push beyond the limitations of the present. The cosmos had shown that its most powerful events speak through many messengers, and now humanity knew how to listen. The success of GW 170817 did more than confirm long-standing predictions. It also revealed how much more could be learned once multiple messengers carried information from the same cosmic event. As scientists examined the combined data, they began to understand how gravitational waves and electromagnetic light complemented each other, each filling in gaps the other left behind. Gravitational waves revealed mass, geometry, and orbital motion. Light revealed temperature, composition, and environment. Together, they showed the universe through two entirely different senses. For the first time, astronomy had stepped beyond the limits that had defined it since ancient civilizations first looked at the night sky. The gravitational wave signal from GW 170817 contained subtle features that drew the attention of nuclear physicists. The tidal deformability of the neutron stars, encoded in the changing frequency of the inspiral, reflected the stiffness of matter in their interiors. A stiffer equation of state would produce stars that resisted compression more strongly. A softer one would allow greater deformation under tidal forces. These differences left faint imprints on the gravitational waveform, tiny deviations in how the stars approached one another before merging. Although the signal was not strong enough to provide complete answers, it narrowed the range of possible equations of state. It ruled out models in which matter was too stiff, and it challenged theories that predicted overly soft cores. This constraint represented progress in understanding one of the most extreme forms of matter in the universe. Meanwhile, the gamma-ray burst provided insight into the moment of collision. Short gamma-ray bursts had long been associated with neutron star mergers, but the exact mechanism behind these bursts was still debated. Observations from the Fermi telescope showed that the burst following GW 170817 was slightly weaker than some predicted models, suggesting that the relativistic jet produced during the collision was not pointed directly at Earth. This subtlety offered a clearer picture of how gamma-ray bursts are structured. They are narrow, powerful jets that can appear extremely bright when aligned with the observer's line of sight, but significantly dimmer when viewed from an angle. This helped explain why many neutron star mergers likely occur without producing detectable gamma rays. The absence of light does not imply the absence of a merger. It simply reflects the orientation of the jet relative to Earth. The kilonova provided another layer of information. As the newly formed heavy elements decayed, They emitted light that changed color over time. Early optical observations showed a bright blue component produced by elements with low opacity. As the days passed, the emission shifted toward red, as lanthanides and other heavy elements absorbed more of the shorter wavelengths. This evolution matched theoretical predictions with striking accuracy. It confirmed that neutron star mergers were powerful sites of R-process nucleosynthesis, the same process responsible for creating most of the heavy elements in the periodic table. The kilonova served as a direct demonstration of the universe's ability to forge complex atoms in violent cosmic events. Radio and X-ray observations continued to reveal new details long after the initial burst of light faded. Radio telescopes tracked the outflow of material expanding into interstellar space. The speed and structure of this flow allowed scientists to determine the energy contained in the ejector and the angle at which the jet was pointed. X-ray observations revealed the behavior of shock waves as they propagated outward. These afterglows built a timeline extending far beyond the initial collision. They painted a picture of how the debris evolved, how it interacted with surrounding gas, and how the event's energy redistributed across the environment. Together, these observations formed a new kind of measurement, one that tied microscopic processes to macroscopic events. Nuclear reactions inside the neutron star debris cloud shaped the light curves seen in telescopes. The geometry of the merger, inferred from gravitational waves, determined how jets formed and which directions they traveled. The expansion of the ejector traced the physics of high-energy plasmas in the aftermath of the collision. Every layer contributed to a single, coordinated story. The event also reinforced the value of synchronized global coordination. When the gravitational wave was detected, teams across continents responded in minutes. Robotic telescopes scanned large swaths of the sky, searching for the kilonova's faint glow. Space-based instruments recorded high-energy emissions. Radio arrays pointed toward the source, even before optical confirmation arrived. This level of cooperation had been anticipated for years, but GW 170817 demonstrated that it was not merely possible, but essential. Multi-messenger astronomy required the combined effort of many observatories working as a single system. Beyond the observations themselves, the event underscored the reliability of general relativity in yet another regime. The gravitational waveform matched predictions from Einstein's equations with extraordinary precision. The timing of the gamma rays confirmed that gravity propagates at the speed of light, ruling out a wide range of alternative theories that predicted differences in propagation speed. Even the behavior of the remnant object, which briefly existed as a hypermassive neutron star before collapsing into a black hole, aligned with predictions from numerical simulations. The consistency of these results strengthened confidence in the fundamental principles that had shaped modern physics for more than a century. Yet GW 170817 also opened new questions. How often do neutron star mergers occur? How does their frequency vary across cosmic time? Are they the dominant source of heavy elements, or do other processes contribute significantly? How do the internal magnetic fields of neutron stars influence the formation of jets? What determines whether a merger leaves behind a temporary massive neutron star or collapses immediately into a black hole? These questions were grounded entirely in evidence, each arising from the details of the observed event. None required speculation beyond what the data supported. They represented the next steps in a rapidly expanding field. As the analysis continued, scientists recognized that multi-messenger astronomy had fundamentally changed the structure of astrophysical research. The boundaries between disciplines began to dissolve. Astronomers, particle physicists, nuclear theorists, and cosmologists collaborated more closely than ever. A single event could carry information relevant to all of these fields. Gravitational waves became a bridge linking them together, and as more detectors joined the global network, the range of observable events would grow. The universe had shown what was possible, and now humanity was preparing to expand its reach. This part of the chapter marks a period of profound transformation. The lessons of GW 170817 extended far beyond the event itself. They reshaped how scientists observe, how they coordinate, and how they interpret the cosmos. Ahead lay deeper discoveries and the continuing refinement of the tools that made these breakthroughs possible. The lasting impact of GW 170817 was not confined to its immediate scientific results. Its true significance unfolded over months and years as researchers continued to study the event and integrate its lessons into the broader structure of astrophysics. The world had witnessed the first full demonstration of multi-messenger astronomy, and this accomplishment reshaped the scientific landscape in ways that extended far beyond gravitational wave detection alone. It influenced the design of future observatories, inspired new theoretical frameworks, and revealed that the universe was far more connected across different channels of information than earlier generations had imagined. In the aftermath of the discovery, researchers examined the gravitational wave data with increasing scrutiny, refining their measurements of tidal deformability and improving their understanding of neutron star interiors. The waveform carried the imprint of how matter responded to extreme gravitational forces. Slight variations in the frequency evolution held clues to the internal stiffness of neutron star material. These clues were subtle, but they narrowed the range of possibilities in measurable ways. The event demonstrated that gravitational waves could probe nuclear physics directly, providing constraints that rivaled those obtained through particle accelerators and nuclear experiments on Earth. This connection between astrophysics and nuclear theory strengthened the collaboration between fields that previously operated largely independently. Meanwhile, continued electromagnetic observations built a more complete picture of the event's aftermath. The kilonova's fading glow revealed how heavy elements cooled and dispersed through the surrounding environment. By comparing the observed light curves with theoretical models, scientists learned how different isotopes contributed to the brightness at different wavelengths. They traced which elements formed in the earliest moments and which emerged later as the expanding matter underwent further transformations. These observations did not merely confirm the production of heavy elements. They quantified it, showing that neutron star mergers could produce significant fractions of the gold and platinum found throughout the universe. The gamma-ray and X-ray observations also played a crucial role. They allowed scientists to reconstruct the geometry of the relativistic jet, showing that it had been launched at an angle slightly misaligned with Earth's line of sight. This helped explain the relative faintness of the gamma-ray burst. It also demonstrated the importance of viewing angle in interpreting cosmic explosions. Many similar events could occur without producing detectable gamma rays simply because their jets pointed elsewhere. Gravitational waves, however, were not limited by such constraints. They traveled in all directions, offering a way to detect events that traditional telescopes might miss entirely. The radio afterglow presented another layer of insight. Over months, radio telescopes tracked the outward-moving shock wave as it interacted with the surrounding interstellar medium. This allowed scientists to measure the density of gas around the merger and to reconstruct the history of the system before the collision. These details helped determine whether the neutron stars had formed together in a binary system or if they had come together through dynamic interactions in a dense stellar environment. The slow evolution of the radio signal served as a long-lasting witness to the violent event, revealing information that gravitational and optical signals alone could not provide. As the observational campaign unfolded, the event encouraged a re-evaluation of the rates of neutron star mergers across the universe. Prior estimates had been uncertain, derived indirectly from the number of known binary neutron stars in the Milky Way. The detection of GW 170817 provided the first directly measured rate based on gravitational waves alone. This rate helped refine models of galactic chemical evolution. If neutron star mergers were as common as suggested, then they could indeed contribute substantially to the inventory of heavy elements across cosmic time. If they were less common, then other processes, such as rare types of supernova, might also play significant roles in forging heavy elements. The event did not settle this question completely, but it provided essential data for future studies. At the same time, the impact of the event extended into cosmology. The distance measured from gravitational waves combined with the redshift obtained from the host galaxy created a new type of distance measurement independent of traditional methods. This strengthened the effort to use gravitational waves as standard sirens, offering a complementary path for determining the expansion rate of the universe. As more detections accumulated in the years that followed, standard sirens became an increasingly important tool for addressing the ongoing Hubble tension, one of the most persistent mysteries in cosmology. The collaboration that produced these discoveries represented a remarkable moment in scientific history. Researchers from around the world participated in the analysis. Observatories coordinated across continents. The flow of information was rapid, transparent, and collaborative. Multi-messenger astronomy demanded this unity, and the success of the campaign demonstrated that such coordination could be achieved on a global scale. It created a new standard for how science could be conducted in the 21st century. Instead of isolated efforts, discoveries emerged from interconnected networks that combined the strengths of diverse instruments and disciplines. The long-term effects of GW-170817 reshaped the design of future gravitational wave detectors. Scientists recognized that improved sensitivity would allow deeper exploration of neutron star physics. They planned upgrades that would reduce thermal noise, increase laser power, and enhance mirror coatings. They discussed new facilities that could detect even fainter events, reaching farther into the universe and capturing mergers from earlier epochs of cosmic history. The event inspired proposals for detectors in space, where environmental noise would be minimal and the arms of interferometers could stretch for millions of kilometers. These future missions, such as the Laser Interferometer Space Antenna, would open new frequency bands and allow detection of systems inaccessible from the ground. As the analysis of GW-170817 reached its conclusion, the scientific world understood that it had witnessed the beginning of a new era. The event showed that the universe speaks through gravitational waves, gamma rays, optical light, infrared glow, X-rays, and radio pulses, each revealing different aspects of the same reality. Multi-messenger astronomy was not a temporary phase. It was a fundamental transformation. It unified disciplines and provided a new foundation for studying the cosmos. This chapter marks the culmination of a journey that began with Einstein's prediction more than a century earlier. Gravitational waves had moved from theory to detection, from detection to discovery, and from discovery to a complete integration with all forms of astronomical observation. And now, the world stood ready for a future in which these waves would be measured routinely, each one adding another layer to the expanding understanding of the universe. Ahead lay deeper challenges and greater discoveries. With every improvement to the global network of detectors, the universe would reveal more of its hidden structure. And with each new signal, humanity would refine its portrait of the cosmos, guided by evidence and united by the pursuit of understanding. For more than a century, Einstein's general theory of relativity had guided the understanding of gravity. Yet its true strength only became visible when gravitational wave detectors began capturing signals from the universe's most violent events. With every detection, the theory demonstrated its remarkable precision. The masses and spins of merging black holes unfolded exactly as general relativity predicted. The in-spiral patterns, the moment of collision, and the final ring-down behaved with mathematical consistency, even in regions where space-time curved so strongly that no earlier experiment could have reached. These observations extended Einstein's insights far beyond the solar system tests that had once been considered the gold standard. Now the theory was being validated in the hearts of black hole mergers, where gravity shaped time and geometry in ways no human had ever directly observed before. Yet the journey to this confidence had not been smooth. Einstein himself had questioned whether gravitational waves were real, and debates in the early 20th century reflected the difficulty of interpreting the mathematics. It took decades of theoretical clarification and indirect evidence from binary pulsars before scientists accepted gravitational waves as a physical phenomenon. When the Hulse-Taylor pulsar revealed orbital decay exactly matching the predicted loss of energy through gravitational radiation, the community gained its first strong confirmation. But it was not until detectors finally recorded gravitational waves directly that the full depth of Einstein's prediction became undeniable. Each new event strengthened this understanding. The speed of gravitational waves, measured through the remarkable near simultaneity of GW 170817 and its accompanying gamma-ray burst, proved identical to the speed of light to astonishing precision. The polarization of the waves matched the two modes predicted by general relativity. The conservation of energy during mergers, visible through the mass lost to gravitational radiation, aligned perfectly with the equations set down in the year 1915. Even the silhouettes of black holes observed by the Event Horizon Telescope matched the structure expected from the theory. But beyond the celebration of accuracy lay a deeper recognition. General relativity continued to succeed because it captured something fundamental about the universe. Gravity was geometry. Mass and energy shaped spacetime, and spacetime guided the motion of matter. This geometric truth revealed itself in every detection, from the subtle tidal deformations of neutron stars to the violent collapse of merging black holes. Yet the closer scientists came to confirming Einstein's view, the more clearly they saw the limits of what remained unknown. The theory thrived in strong fields, but it did not explain the interior of neutron stars, the earliest moments of the universe, or the quantum structure of spacetime. Its success did not close the frontier, it illuminated it. And in that illumination, the next questions began to take shape, guiding the path toward deeper understanding. As gravitational wave astronomy matured, the boundaries of the known universe came into sharper focus. These limits did not arise from speculation, but from direct observation. They emerged from the noise floors of detectors, from the faintness of distant events, and from the incomplete catalogue of signals recorded so far. Each unanswered question was tied to real data, not to imagined possibilities. The universe itself defined the frontier, marking precisely where understanding remained incomplete. One of the clearest limits involved the interiors of neutron stars. Tidal deformability measurements had narrowed the allowable equations of state, yet the exact nature of matter at extreme densities remained hidden. Whether neutron stars contain purely hadronic matter or layers of quark-rich material remained uncertain, not because of hypothetical physics, but because current signals lacked the fine detail needed to distinguish one model from another. The population of black holes also raised evidence-based questions. Gravitational wave detectors revealed many black holes heavier than those previously known from X-ray binary studies. This indicated that low metallicity environments or dynamical formation channels played significant roles in producing massive remnants, but the exact distribution of these environments across cosmic time remained unclear. The spins of black holes further complicated the picture. Some systems showed aligned spins consistent with isolated binary evolution, while others exhibited misalignment indicative of dynamical interactions. These patterns pointed to multiple formation pathways, but without larger catalogues, the proportions remained uncertain. Another frontier involved frequency limitations. Ground-based detectors could not detect the slow spirals of supermassive black holes, which produced waves at nanohertz frequencies. Pulsar timing arrays had recorded hints of a gravitational wave background in this regime, but the signals remained unresolved. Similarly, intermediate mass black hole mergers lay beyond the sensitivity of current detectors, hidden in a frequency range between those accessible from Earth and those suitable for space-based observatories. Even propagation tests carried limits. All observed gravitational waves traveled without dispersion, matching Einstein's prediction. But these measurements were bounded by detector precision. If tiny deviations occurred over billions of light years, they lay below the threshold of current instruments. The absence of anomalies did not prove their impossibility. It marked the limit of present measurement. Each of these boundaries formed a concrete and scientifically grounded map of the unknown. The universe was not mysterious because of speculation. It was mysterious because the instruments had not yet reached far enough, deep enough, or sensitively enough. And this recognition set the stage for the next generation of gravitational wave observatories, which would extend the frontier and transform these limits into discoveries. The future of gravitational wave astronomy had already begun to take shape, not through speculation, but through approved missions, active construction, and global collaboration. The next era would widen the observable spectrum of gravitational waves, reaching frequencies and distances beyond the capabilities of current instruments. This expansion would not reinvent physics, it would amplify the universe's voice. The laser interferometer space antenna, known as LISA, would open the millihertz window, revealing supermassive black hole mergers, extreme mass ratio in spirals, and thousands of compact binaries within the Milky Way. With spacecraft separated by millions of kilometers, LISA would detect waves too slow for ground-based detectors. These signals were not hypothetical. They were predicted by decades of observations of galactic centers, population models, and stellar evolution theory. On Earth, the Einstein telescope and the Cosmic Explorer would push sensitivity deeper into the high-frequency band. With longer arms, improved materials, and reduced noise, these detectors would capture mergers from earlier cosmic epochs and observe neutron star in spirals with far greater precision. Their underground and long baseline designs were direct responses to the limits identified in current detectors, ensuring that the next generation would reach frequencies and distances previously inaccessible. Pulsar timing arrays, enhanced by the coming square-kilometer array, would probe the nanohertz band with unprecedented precision, transforming the current gravitational wave background into a resolved and structured map of supermassive black hole binaries throughout the universe. Together, these observatories formed a continuous spectrum. Nanohertz waves from orbiting giants, millihertz waves from massive inspirals, and kilohertz waves from compact mergers would all become part of a unified gravitational sky. For the first time, humanity would have the ability to observe the full gravitational history of the universe across scales stretching from the remnants of stars to the hearts of galaxies. This future was not speculative, it was being built, and with each detector added to the global network, the universe's voice would become clearer, richer, and more complete. As gravitational wave astronomy approached its next era, a quiet realization took hold. The universe had been speaking through spacetime since its earliest moments, long before stars existed, long before galaxies formed, and long before light filled the cosmos. Every collision, every orbit, every flicker of gravitational motion had rippled outward, carrying information across unimaginable distances. Now, for the first time in human history, instruments were finally sensitive enough to hear these ancient vibrations. Yet the most profound truth lay not in what had been detected, but in what had not. Beneath the recorded signals, beneath the catalogue of black hole mergers and neutron star collisions, beneath even the faint hum observed by pulsar timing arrays, there existed an ocean of gravitational waves that no current detector could reach. These waves were older than galaxies, older than stars, older than the cosmic microwave background. They carried traces of the universe's first motions, the earliest patterns written into space-time when everything was still young and turbulent. Their existence was supported by theory, by cosmology, and by the simple logic of gravitational radiation. They were not speculative, they were real, traveling still, untouched for more than 13 billion years. But they were faint, delicate, hidden beneath the noise floor of every instrument built so far. What secrets did they carry? What stories did they tell? What signatures of the earliest physics were encoded in their structure? As detectors grew more sensitive, the frontier would shift. One day, perhaps centuries from now, instruments might finally touch these primordial waves. They might reveal how the universe expanded in its first moments. They might uncover the earliest patterns imprinted onto spacetime. They might show whether matter and energy behaved differently in those ancient epochs. And they might expose subtle features of spacetime that no present theory had yet described. This was the final mystery left in the arc of gravitational discovery. Not a contradiction, not an anomaly, but an echo from the beginning, waiting for ears sensitive enough to hear it. The universe is still speaking, and somewhere, faint but unbroken, its oldest message is still on its way.